इसको अगर ऑन करके जाएगा लंच करने तो भी
What's it?
to keep it on during the lunch.
Lunch.
Yeah.
Okay. I have to cover the lunch minimum. That's why I'm saying.
No, you can go, let it be.
I have to cover it video footage of there. That's why I remove the camera. Otherwise, you
So
do.
whenever you, every time you will remove it will change.
Yes. If you don't want to cover the lunch and dinner, whatever maybe, I will stand there the camera here only.
Welcome back to the technical sessions. I now request Professor N. Sir from the Department of Chemistry to just detail about the technical sessions to your audience.
Good morning to all, and once again welcome to International Conference on Smart Nanotechnologies. This is the most important part of any conference, the technical sessions. So I hope in the auditorium, most of them are students. There are two special announcements to students firstly. I request all the students concentrate on each and every talk that is presented in the technical sessions. Note down the important points, and we have already briefed you in the classroom, and utilize this conference to get knowledge. That is the basic objective. Technical session means simply sitting and you are hearing like anything, just like a song. It's not correct one. I request all the PG students, UG students, please utilize this opportunity and get the knowledge. Ladies and gentlemen, this is the technical session 1. We have 4 important talks here. And these talks are divided into categories: keynote talks and annual talks. All the eminent personalities are already in the know. They are going to tell you the different aspects of smart nanotechnology. And for keynote, I request the keynote speakers, please limit your speech by 30 minutes. And 5 minutes we are going to give you for Q&A. And for invited talk, We are going to give you 25 minutes and 5 minutes for Q&A. This question and answers will be given priority firstly to the students. Please reserve your questions. The time comes, you can ask your question and get the clarification. With this brief details, I once again request Dr. Hans to proceed the session 1.
Thank you, sir. I now request the moderators of the session 1, Professor Khalifa Al-Sabri, Head of the Department of Civil and Architecture Engineering, Sultan Qaboos University, Sultanate of Oman, to raise the dais. And I also request Professor P. Srinivas Rao, sir, the Head of the Department of Chemistry, Dr. Vishakhapatnam, also to raise the dais. These two people will be acting as the moderators of this session. It's time now for the keynote lecture by Professor Jaeman Kim, Director, Creative Research Center for Nanocellulose Future Composites, South Korea, who is the chief guest of today's event. And Sir will be sharing a talk on the title Nanocellulose and its Applications for Smart Devices and Structures. I request Sir to take up this presentation.
Thank you, moderators and chairperson for this introduction. Today I'd like to introduce what we have done during the last 20 years for nanocellulose. And since this talk is very long, I'd like to briefly introduce this if you the question title after this talk. So first, to introduce nanocellulose and smart devices that we have developed with nanocellulose. The photon shape is one of the application. Stripping, how we can deal with stripping for structure in nanocellulose and structure application. We have our society faced greenhouse gas emissions problem. What interesting is 20% of greenhouse gas emission is from material, which covers steel and cement, but 30% of greenhouse gas emission is for plastic. So we to achieve non-zero greenhouse gas emission by 2050, we have 30 years left that we can play. So we need a sort of new material that can come up with greenhouse gas emission. So we can bring new idea from the non-specified material with the cost of cellulose, lignin, and access technology wood trunk area. It is because of wood fiber, which is mainly 50% cellulose and 25 lignin and cellulose. We see wood fiber is has structure of macro and microfiber, non-cellulose fiber. You see the cellulose fiber has crystal part, so-called cellulose crystal, and we call this cellulose fibers microfiber. And then you see this graph here shows last So metal, plastics, and composites there. Interestingly, the nanocells locate high position compared to other materials. It means nanocells has a very unique characteristics. It's renewable and can meet net zero greenhouse gas emissions, but also it has very high specific strength and low density and very low thermal expansion coefficient. It's very thermal stable material. So we believe that these nanocells can be a building block for sustainable future material. They can substitute the carbon materials. With this excellence of nanocells, we can apply this material for many areas, including electronics and sensor actuators, biomedicines too, automotives and aerospace and structure, textile, energy devices, and packaging, etc. So I'm not going to show you all of this, but some application-oriented things should be will be reported. How we can isolate nanocellulose? There are many ways. Possibly we can use chemical to isolate nanocellulose, but when you use chemical, we need a lot of chemicals. So to use the chemical dosage, we combine the chemical and physical method. By temp oxidation, we weakly treat pulp, the swell pulp, and then use the so-called aqueous collision method, which is physical method. They use 200 megapascal high pressure water that collide each other and by applying shear force, you can efficiently isolate and fiber. Those are photographs of cells on the fiber isolates from hardwood, softwood, bamboo, and cotton pulp. And this F image shows the isolated on fiber size. When we characterize the size, you see here, the cell length is about less than 1 micron. And then when you measure the diameter, they range from 21 to up to 37 nanometer. We measure Young's models by using what's a force microscope using it for many tests. It's very, very difficult, but a lot of work and measure. Characterize, as you can see, the small range above A up to 1 of your mass, which is less than theoretical Young's model of nanocellulose, which is 1/50 of Pascal. So which is very difficult, and you can see that this material is highly strong and highly elastic material. So I'll show you some device applications. There are many device applications that you can play with this nanocellules, field detector, chemical sensor, and soft actuator, biosensor. We made close sensor and tactile sensor to shock of sensor. That's not optics. We show you some of them. We first made sensors and speak the capabilities exact same some faces and the view of this cell is a field eye. Now there is no magnetic coil. It very compact and produce a lot of sound vibration. Next one is banding is for actuator. This actuator can move by applying very small electric field, much less than the actuation in room temperature condition. High stable. Also, with this, actually made a remote driven actuator. So, integrate rectifier and then change microwave, convert this power and then control the circuit here. Integrate the red panel here. And this is actuator and cellulose. We put a small amount of RIT and component to enhance the migration effect. So this is the remote driven Wi-Fi way. And we also combine the nanocellulose with carbon nanotube, molecule and single carbon nanotube by bonding carbon nanocellulose. And then they make a correct resistance, which can I didn't show you the detail of this correct resistance. It's very small ppm of temperature, like ethanol and alcohol, etc. With this carbon nanotube, the cellulose made field transistor. Cellulose itself is insulated, doesn't make negative field. By adding very small amount of carbon nanotube, can make it conductor or semiconductor. So there is some pressure. So by blending very small carbon nanotube, we can make electrophilic to be between the carbon and make a field transistor. This shows the result. And then we call it this graphite oxide. Actually, this work has been done by a official technical. And then we by calling the this graphite oxide on top of cellulose filament with electrical pattern, give me the flexible can show the signal without touching. Once you can close your finger, you can show the signal again. So this is what goes by the impedance of finger that goes to when you close the finger to the leg. Impedance change and shows this signal. It's very positive for touching. Without touching, you can release. Next one is lens. You can imagine what happens if you can change the focal length without changing the distance by changing the conventions. By changing the reflection index or by changing the curvature, then we can actively tune the lens like human eye. This kind of eye is very process for smart optics and projectors. So we synthesized polyurethane with cellulose crystal. First, we used cellulose crystal blend the PDGA as polymer, and then you estimate you can see the June in and out by applying electric field. Then you see the transmittance quite transparent. Keep in mind, nanocellulose is really transparent. Okay? So it's very good for optics application. The reason why when you see the wood color is dark brown or black, that's not the cellulose color, but the lignin. So when we test the actuation behavior of this material under the 3 kV per millimeter distance, because 10% strain, it's a huge strain on the low actuation voltage. Okay? This 3 kV per millimeter is almost 100 times less than the well-known dielectric national actuator. So it's very interesting. I'll show you another one. We measure the optical behavior is so-called CPPU, that's a CNC blended polyurethane. What I did was we first sent a reference signal and then compare the transmitted signal through this CPPU. This shows some interference. That means sometimes the reflecting index change in this material. So by numbering this interference, you can calculate this reflecting index change. Although it's very small, but we make only 2 difference change. This is a interesting idea. Why does this reflecting change negatively? So we have three configuration. One is this is the CPPU, and then you put the distance and apply to the angle. And this is the second configuration. We put the touch point between the electrode and the CPU, and then you put spacer, doesn't move error, and then put them together with the CPU. So you see configuration tested, actually we have. The fourth configuration shows very small reflecting. It doesn't say error. But configuration 2 shows the reflection is decreased the electricity, but small. Configuration 3 shows high efficiency. That means the reflecting index is going to change. Indicates that we can choose the reflecting index by applying electricity. This reflecting index tuning is very important for smart. We are changing curvature, we can tune, we can change the focal length. Let me move on to smart optics application. One is the potency. Potency is the planar lens used for light and space. So it has just like planar lens. It's simple coarse disc has many pinpoints. So when a light comes in, it assists the pinhole has different size with the same length. You don't need the refraction. But it's add the ball and then make this focus. So this point-based potency is used for light. Satellite. But it's heavy. If you want to have a large size potency, it's almost impossible to carry with the rocket. So NASA is trying to deploy potency maybe are trying to make this membrane potency with some polymer quality. But probably even this is managed high temperature. This is not suitable for specification. So we propose to use non-surface for non-surface in temperature. So we design the potency is a small size one, we not like the sensitive United States. And this is potency all size. This is formats for potency. The potency that or that is dependent on the wavelength. When you see this is the effectiveness, the scale depends upon the direction change a little bit. But when you take this range and see the wavelength around here, 532 target length, that's the thickness of 1.55. And we decided this depth 484. And then make this more than the PR. This is 6.4 mass more than the PR more, and then put the cellulose film. This is cellulose film, like fabricated, the large size or the small size or many major density about less than 500 nanometer for that. And then since in space, the low Earth orbit, the vacuum condition is very severe, 10 to minus 10. So we made this vacuum chamber and test what happened in this photon sheet. The next vacuum applied this chamber is very near to the low Earth orbit vacuum condition. And then measure the pinner depth and home port position here. So in average, it's less than 5%, which is acceptable for engineering strength. And then measure the characterize the photon sheet using this laser beam. Unfortunately, we didn't have the 5 nanometer laser green light at this time, so we used this one. And they show that it can shoot the focus beam, and then you see the beam profile is shown here. So then we move on to silk printing. Silk printing is sort of now there's a new technology that can make armature structure. So for many people use lactic acid, some pattern-based polymers for printing and make armature structure. But we need to make the modified structure, sustainable structure, because as I mentioned, we need the meet natural greenhouse gas emission. So many people, some people try to print nanocellulose, but they most focus on low concentration. The problem with low concentration is the solid content has a low solid content. When dry, there's very, very large shrinkage. When the concentration of over 10% still has large concentration shrinkage here and low chemical properties. So one of my students, PhD student, he just finished PhD last month. He did this high concentration nanocellulose printing. It's very challenging. So he did all setup of this printing machine, and then used bio-based process linker. Two process linkers. One is post mixed cells on fiber crystal. And then add polymer and acidity that can connect cells and crystals on fiber and make the bond. This composition is a lot of since concentration. And the soil content of this one is over 4%. And then make this paste. It's not a fluid paste. And then use this extrusion machine to extrude non-sterile paste. And then dry. Okay. Post-finish type phenol without torus maker. As you can see, after printing and dry shows the denomination between layers. By adding maker, you can keep this shape. This is the cubic shape, and then the partial divided, and then this is the pure one, and then this is the added one. You can see denomination happen. This is pure one. This is scaffold for bioidentification. Okay. For example, we can use this scaffold for more substitution. This figure shows the S1 happen in this video cells. So it shows section curve and cross section image of the printed one here. This is a solid second bond between the different layer. It is high chemical property. So 110 megapascal, which is quite high compared to other different another. We characterize the shapeability by measuring the size shrinkage before, just after the printing and after the drying. You can see there's some shrinkage less than 50%. Much less than the previous report. Next, we blended citric acid. Citric acid is bio-based linker. Especially for the tiniest one. I didn't bring the tiniest here, but tiniest is very good for outside characteristic for fish for bioidentification. Again, blended narcissistic reaction did the same process. It shows the citric acid is S1 after expression. This photograph shows the bond here. This is the strong bond between the non-cells. Again, when I measure the mechanical properties, it shows nearly 82. This is the crush test. Keep in mind, crush test and the hazard is a bit different. Crush test is into Pascal for models about 7 gigapascal. Again, it shows quite secure and easy between the printed layer. We characterize this with first printed outer shape with this citric acid blended non-cellulose, and then characterize the shape fidelity. The shape fidelity about the same as PPA. Last one is printing a piezoelectric bevel by printing non-cellulose. This is a lead 0.5 power level for piezo ceramic to print. And the other hand, piezo polymer like PVDA polymer fluoride is very flexible but piezoelectric. properties law. So we try to let the PDT power with another system and make the case that the case this is the law for concentration more likely suspension. And then clean up after drying. We put and then drying in the 40 legs for the both sides. We put into very high negativity to align peace power and ourselves. So if you want quite Tesla main period. So this is quickly the stage, the sketch, and then the drawing. It's quite so like it's not a bit goes now or and then put this prefect one the body actually put this superconductor membrane to align the electric power. The question this is not now for electric is not supply along the electric and then pop to the magnetic. This alignment is very important to improve the period electric behavior and technical property of the this action graph shows the several stages here. This is the crystals here. Those peaks are each piece. As you can see, this third quadrant piece shows the cells and each piece appear. From this, we can calculate the surface index of those two pieces. As these piece contents increase, the alignment discussing this increase. The time is increase speed. This shows the young models by high and the toughness very high. Quite the graph. Keep in mind this period charge constant penetration is quite high, or 40, 50 currently. Then a higher constant is very promising and with low error loss. So this table compares all what the provided is 20 with failure. The cancer strength here much higher than the indicator. Now smaller higher than failure. That constant much higher than 54. This one is distancing most of it. It's very flexible, but this one is less flexible. So we believe that this building material can be applied for many smart devices. We have applied this device yet. We just finished this work and then submit the paper. Then we briefly touch. Only 5 minutes more. Structural part. In all industry, there are two issues. One is environment and fuel efficiency. Once you reduce the weight by half, then you can increase the fuel 40%. So decreasing weight is very essential in all industry. At the same time, another issue. When you use steel and metal, there's a lot of gas emission burden. So So we need to develop environment-friendly structural composite. How we can make them from this wood, you can isolate and separate, and using nanotechnology, you can build it up for long-term fiber. At the same time, you can modify lignin as resin, bio-based resin, and then by using them together, you can come up with another strong fiber, reinforced structural part. We establish this product system for resting on cellulose to make the filament, long filament called cellulose, CNF long filament, so for CNF. When stretched to 20%, it gives a young modulus almost 40 Pascal and half Pascal tensor strength, quite high. And then we try to coat on top of filament using SPC resin, polymer alcohol and stretching lignin resin. See here, the resin case detect properties here, and the tensor strength nearly 700 Pascal young modulus, over 30 Pascal. And then we developed bio-based resin. There are two kinds of bio-based resin, the epoxy one and non-epoxy one. So non-epoxy one is synthesized in vanillin is a derivative of lignin, and then made epoxy by the epoxy, derived epoxy from alcohol epoxy one. And then by blending lignin with other biopolymer like PVDA, like citric acid, starch, we developed the bio-based non-epoxy resins. I'm going to show one of this case. First, the one epoxy from lignin, lignin is so complex that it's very difficult to synthesize. Instead, you use vanillin, it's derived from lignin, and epoxidized TBA, and then made a synthesis of an epoxy one. Use the DDM as a hardener, and then make vinyl epoxy and thermal thread. Then this FTR shows the epoxy ring disappeared here. The DDM are maturing. The original epoxy ring appeared here. And then with this, we tested the adhesion strength between the cellulose and this epoxy one by using a lab schedule test. As you can see here, this is commercial epoxy, and this is synthesized epoxy one. Shows more high bond than this commercial, which gives higher bonding strength than the commercial. With this synthesized epoxy and then developed the filament, we made the mat and then use this synthesized epoxy one, and then impregnate resin into the mat using the vacuum moisture resin transfer molding technique, and then after putting them together, pressing, we made the composite. This is the main test of the composite one compared to resin, the high tech properties. It shows the high, good adhesion between the filament and the resin here. Again, we blended this non-epoxy one, polymer acid lignin blended resin. We blended, and this graph shows the adhesion, estabon, active esterification of the resin. And tested the adhesion properties here. Mechanical property of the resin, you see, shows a high elastic modulus of the 6 Pascal and high toughness, and then the strength quite high. Interestingly, the water content is quite high. It's rated above 100 degrees. The main composite, as you can see here, this shows the shell filament and the resin here. It shows good adhesion with above 3 at 60 megapascal tank strength. It shows the good body.
2 minutes, Prof.
It's almost done. This graph shows, table shows the fire region. You see fraction modulus above near 40 gigapascal, and then strength is 360. I'm sorry. So shows the high especially first strength compared to other materials. So we believe this structure is quite strong. So in summary, I believe that the non-cellulose is not only one specific area application, but it can apply. I didn't touch biomedical application in this presentation. We did a lot of work also for biomedical application, so there are a lot of chances, opportunities there. Okay, thank you for your attention.
Thank you, Professor Ken, for your really impressive presentation. Now I think we can have 1 or 2 questions, short questions. Yeah, please.
I came to know that this is it's elastic modulus is comparable to high strength steel. So I need to know that is it useful as a structural material? There is the HSL high toughness. Okay. And similar to that, this is also having high toughness. Okay. And the last modulus can it be used as a structural material? Number 2. For MFC, can it be the substitute of C and D?
First question, we aim at developing a friendly, strong structural material. So the density of steel is 7.3, but this one is 1.4, much lower than the steel. So Jordan won't come and contact me and we have discussion. We cannot fully substitute our structure with this because there's some part very important for collision structure, like the body frame, for example, food and car or fan car can be made with this tool. So because when we also use stains, a lot of bottom in our situation, they have to find substitute alternative. So this one can be an alternative. And then about MMSA, and then how much we do. Again, when you synthesize how you have had a lot of it, then also put a lot of translation. But this one is ordinary of nature. Of course, we use some and isolate ourselves, but still less greenhouse gas emission than carbon. So in that sense, I think this is not as a magnetic.
Last question.
Hello. I follow nice talk of the first question is about the key component or the mechanism of the change of reflective physics in the electric polyurethane. This is the first question. And then second question that I've done about the word of nanosensitive. Have you say the effect of the different magnetic extreme physical things that the space. Thank you.
I think because I mean let me clear this. So first question, the reason why effect change is because of rotation of nanocellules, presence of activity, and then there's a sort of interface provided happen between the nanocellules and then matrix particle. That's the main key. And then second one, I think we can discuss later this at all. It's a pigment-based one, the membrane-based. We use the same nanocellular size, there's no change, by casting with different hole size.
So you have different
Yeah, the hole size, yeah.
Okay, thank you so much, Prof. Ken, for your presentation.
On behalf of our next committee, I request moderators to give a memento to Professor Key. Please give a big round of applause.
Thank you.
Now we have an invited speaker, Dr. Assistant Professor at IIT Jodhpur, India. I request sir to come up on the dais. Dr. is currently working as an associate professor at the Department of Bioscience and Bioengineering, IIT Jodhpur. His research interests include nanomedicine, biomaterials, theranostics, and drug delivery. He earned his PhD degree in chemistry from National Tsinghua University 2012, Taiwan, and his postdoctoral studies were performed at National Tsinghua University 2015 and the University of California, Riverside 2017, US. He worked as the Chief Technology Officer for Radiolytics LLC from 2017 to 19 for the development of biometric nanoconstructs for imaging and therapeutic applications of cancer and vascular diseases. He has published more than 45 papers in various internationally renowned journals. Recently, he secured an outstanding research award for his contributions to the field of nanobiotics at IIT Jodhpur for the year 2021. He also secured prestigious CBT Ramananda Biomedical Fellowship for the year 2018-19. He served as a guest editor for various special issues in MPI and Frontier journals. He is currently serving as a review editor for Frontiers in Bioengineering and Biotechnology, Frontiers in Molecular Biosciences, Frontiers in Chemistry, and Frontiers in Drug Delivery journals. I welcome you, sir, and he will be delivering today a talk on engineering red blood cells mimicking nanoparticles for phototherapeutic applications.
Okay, thank you everyone. So first of all, I thank the organizers for giving me this opportunity to deliver some part of my work, which I worked on biomimetic nanoparticles for phototherapeutic applications. And so I would like to take half a minute to show the beautiful and vibrant campus of IIT Jodhpur. So I welcome all of you. If you get a chance to visit Jodhpur, please make a visit to the campus. It is really beautiful. As the title of my talk indicates, photodiagnostics. So I would like to first introduce what exactly diagnostic formulation or diagnostic medicine is. So basically, this is a multifunctional nanoparticle. This is a representative example of a multifunctional nanoparticle in which you have a nanoparticle which is typically of 100 nanometers or less than that. And then inside this nanoparticle, one can have an opportunity to load different types of drug molecules into it, or they can also do different kinds of surface modification. Maybe they can also conjugate different kinds of targeting ligands like proteins, peptides, or monoclonal antibodies in order to facilitate the targeting of diseases. And they can also incorporate fluorescent dyes to facilitate different kinds of imaging modalities. You can also introduce magnetic nanoparticles, tiny magnetic nanoparticles into it to facilitate as MRI contrast agents. And you can also incorporate a gene into it to facilitate as a gene delivery agent. So numerous opportunities can be made with just one simple nanoparticle. And why we say this as a diagnostic is because this is originated from two different terms, which is therapeutics and diagnostics. So that is where this term has originated called diagnostics. And the major advantage of having a separate diagnostic agent injected into the patient and also a separate therapeutic agent injected into the patient, you can just simply inject a diagnostic agent in which you can diagnose the disease and you can also treat the disease, and most importantly, you can monitor the therapeutic outcome of the disease. So it can offer synergism. So obviously nowadays we always look for a better therapeutic efficacy, more efficient diagnosis is needed. Like for example, if we talk about cancer, you want to identify cancer at a very early stage. Like if the tumor nodule is very tiny, that is where, or even at a very single cell level, that is where you want to identify the cancer risk. And multifunctionality, you can also introduce multiple functions into a single formulation. It can also facilitate localized targeting, and it can also have a prolonged effect in the body. And the most important part is these nanoparticles are activated with the help of stimuli. So unless and until you provide a certain stimulus, these nanoparticles are not activated and they cannot do any harm to the body. But you can provide certain internal or external stimulus, like for example, internal stimuli could be pH, or it could be the change in the redox, or the change in the some sort of enzymatic reaction. And the external stimuli could be temperature, or you can use light, or you can use applied magnetic field, or you can use ultrasound to release the payload from the nanoparticle. So the creation of nanodiagnostics is, as I told, it can integrate both imaging and therapeutic functions in a single multifunctional nano platform. So nowadays we are actually looking at a gradual shift from the conventional one-size-fits-all approach to a more personalized medicine-based approach. Now, how to engineer a nanoparticle? You can engineer different kinds of nanoparticles. There are a lot of strategies which are available. You have inorganic-based materials, you have organic-based materials, have biomimetic-based materials. Like for example, I think most of you have heard about gold nanoparticle, silver nanoparticle. So all these are inorganic-based nanoparticles, right? And then you have organic-based nanoparticles such as liposomes, dendrimers, and polymerase nanoparticles, which are more popular for drug delivery applications. And the last class is the biological materials, where you use like some of the examples which I have given here is erythrocytes, monocytes, and even the level 1 mosaic viruses. This is the plant virus. Mosaic virus is the plant virus. So you can actually engineer these biological materials and make it in the form of nanoparticle. So for my next couple of slides, I will be focusing on how to, what kind of strategies are there to engineer nanoparticles out of red blood cells, and what is the advantage and what is all about it. So one of the most important challenges is that most of the chemotherapeutic drugs. So chemotherapeutic drugs are mostly the organic molecules, right? So these are the synthetic drugs, and these are the small molecules. And these molecules, I mean, mostly the chemotherapeutic drugs, once they are injected into the body, one of the biggest drawbacks is that they can be cleared from the body very rapidly. So instead of, once they are injected systemically through intravenous, they need to circulate in the bloodstream, they need to identify where the tumor site is, and then the therapeutic action need to happen. Instead of that, the moment you inject a chemotherapeutic drug into the body, it tries to get cleared by the complete reticular endothelial system, which is comprised of liver and kidney. Okay, so you have the hepatocytes, which are present in the liver, and you have Kupffer cells, and you have skin macrophages, and all these they try to clear the chemotherapeutic drugs from the body instead of going into the tumor. So one of the important challenges is to prolong the circulation time of your drug molecule. So there are various strategies. The same thing goes for nanoparticles also. There are various strategies in order to prolong the circulation of any kind of payload. And one of the important strategies is to pegylate a nanoparticle. So you can actually take a nanoparticle and then put a thin layer of polyethylene glycol with a certain molecular weight, and then you can also attach sort of alpha-peptides, and you can also attach, you can provide a RBC membrane coating, and you can also have a glucoside-like coating. So these, once you do the RBC membrane coating, so the CD47 which is present on the RBC membrane, which is actually will be there on a nanoparticle, and that actually prolongs the circulation of your whole construct and the therapeutic molecule as well. If you look at the recent research trends on RBC mimicking nanoparticles, so here again are two categories of nanoparticles. That means you can engineer RBC-based nanoparticles through different ways. The first way is you can take the red blood cells directly, and then you can mechanically manipulate them, and you can make the nanoparticles out of it, and once you make the nanoparticles out of it, after returning the hemoglobin and all, it is just a vessel. It is like a liposome. So just like liposome is synthetic like liposome, and you are making a natural liposome out of red blood cell. So it will just be a lipid bilayer vessel, like a structure in which you can incorporate or therapeutic or diagnostic agent, whatever you want, your payload into it. This is strategy one. And the second strategy is that you have an inorganic or organic nanoparticle, and then on the surface of the nanoparticle, you provide a coating. So that means you provide a coating of RBCs on the surface of the nanoparticle. So this is called camouflaging. So strategy 2 is camouflaging, and strategy 1 is making nanoparticles out of red blood cells. So if you look at the research trends on for the past decades, you can see there is a gradual increase in the RBC membrane derived nanoparticles, and lot of research is going on in this particular field. And why is this cause? Lot of research is because most of the nanoparticles, the biggest challenge, I think, all of us talk about nanotechnology, but when it comes to the translation of nanotechnology to the biomedical application, one of the biggest concerns is the toxicity. Right? We always concerned about the toxicity, the short-term toxicity, long-term toxicity, and also the immunogenicity. You need to keep in mind all these factors in order to cleanly translate a particular nanoparticle, especially for a biological application. And why people are looking to biomedical nanoparticles? Because they are, like for example, if you take RBCs, ideally, whatever function that normal RBCs do, they also expect that these nanoparticles, engineered nanoparticles of RBCs should also perform the same functions. So that's why these are advantages. Since my talk is on photodiagnostic application, so that means I'm interested in light. Okay? And in particular, I'm interested in near-infrared light. And why near-infrared light is important? Because I think all of you know that, I think all of us are aware that UV light and visible light, they have a very poor tissue penetration in the body. Right? Like for example, if I use a green laser pointer or if I use a red laser pointer and if I touch the finger, I can see the penetration through my skin. Right? So they have a very poor penetration there. But if you look at the near-infrared biological window, so this is called as a biological window because this can reduce scattering and it has high tissue transparency, deeper tissue penetration, and minimal of fluorescence, and you can have improved signal-to-noise ratio. And the most important thing is the biological components, which typically consist of hemoglobin, oxyhemoglobin, and water, and the melanin which is present in the skin. These are the major components. And all these components are very strong in the UV and visible region. So that means the infrared region is completely tissue transparent. So we are interested in developing nanoparticles which can be activatable using near-infrared light. And again, it should be a diagnostic formulation that it should diagnose, it should perform imaging, and it should also do a therapy. Right? And one of the small molecules which I am very interested in is indose-933. Indose-933, it is a carbon dye. And it is just the only FDA-approved small molecule which is used for treating which is used for imaging it is mainly used for imaging eye-related issues. Okay, so this is the only near-infrared light activatable FDA-approved dye molecule. And if you look at the molecular structure of the IgG, it has two lipophilic moieties and hydrophilic moieties. And it can absorb very strongly in the infrared region and it can also emit fluorescence in the infrared region. But if we inject IgG directly into the body, like for example, if you directly inject IgG into the animal, so what happens is that within 1 minute it will go and accumulate in the liver. So that means it gets rapidly accumulated by the liver, and there is an exclusive uptake by the hepatocyte, and over a period of time you can say that the signal is disappearing. So that means IgG as such is a small molecule and has a very poor circulation half-life. So if I inject, like let's say for example 100 milligrams into the body, more than 50 milligrams can get cleared within 10-15 minutes. So this is one of the biggest challenge. So plasma half-life of IgG is very short, and there is an exclusive uptake by the hepatocytes, and most important, this is non-specific. So it can get biodistributed in all the organs. So now here we are trying to develop erythrocytes as a platform for the delivery of optically active agent and that to IgG. So IgG is an approved FDA-approved agent, but it has lot of drawbacks if I use IgG as such. So my idea is to encapsulate IgG into an erythrocyte-derived nanoplatform and then make this whole nanoparticle as a diagnostic agent and make it light activatable and perform optical imaging as well as therapy. So how engineer a red blood cell? So you can always see the whole blood and then you can remove the plasma and the body from the whole blood, and then once you get your RBC packet, you can do the intracranial hemoglobin out of the RBC packet, and then you will end up getting a micron-sized vesicle. Okay? And once you have a micron-sized vesicle, these vesicles can be mechanically manipulated either with the help of extrusion or with the help of sonication process to bring it to the nanocytes. And once you bring the diamond to the nanocytes, you can encapsulate different kinds of optical cargoes into it, and then you can take the nanoparticles out of it. And like ICG, it's a organic dye, so it can exist in both monomeric forms as well as dichroic form. So it can also, some of the molecules can encapsulate into the core of the vesicle, and some molecules can stay on the bilayer as well. And the advantages of such kind of nanoparticle platforms is that the first thing is natural RBCs, they have a longer circulation half-life. So that means ideally, whatever nanoparticles which are coming out of the RBCs should also perform very well. It should not be like 10-15 minutes circulation half-life. And it can be targeted autologically or from the compatible blood types. And it should be easy to scale it up, and you can fabricate using non-exchange temperatures, and the diameter can be tuned. Like for example, we are interested in making nanoparticles out of RBCs, like let's say we want to utilize them for cancer, but we want to utilize them for vascular diseases, treating vascular diseases. You can directly use the micron-sized particles. So the diameter can be tuned. So there is a versatility in the diameter.
2 minutes. 2 minutes.
And then the optical properties can also be very well controlled. So this is how my micron-sized particle look like, and this is the nano-sized particle look like. And you can see the size can be controlled very well, because of 100 to 200 nanometer. And I'm not getting into the details of all the characterization. But once you encapsulate ICG to it, you can look at its optical properties, how stable it is, and all over a period of time. You can look at the stability. And this is looking at the biodistribution of these kinds of nanoparticles. You can see that the micron-sized nanoparticles, nano-sized particles, when compared to those ICG, they can circulate for like until 48 hours. So until 48 hours, they can get in the bloodstream. But ICG will get here within 10-15 minutes. And this is just looking at the biochemical characterization. I'm not getting into the details of the, but the most important part, the photochemistry is the most important part. So you make these nanoparticles light activatable, and so here once you treat these nanoparticles to the breast cancer cells, and you irradiate with 8 nanometer light with 1% centimeter square for 15 minutes, and you can effectively kill the cancer cells with the help of photothermal that is the heat which is being released by ICG through the non-radiative relaxation pathway, and also the photodiode therapy, which is done by the cross generation, which is coming from the ICG. And those can actually kill the cancer cells very effectively. And here we are taking the breast cancer cells. And the other example is you can also image them. You can make these nanoparticles more target specific. So here, in order to target the intraperitoneal ovarian tumors, we have used the folate functionalized ones. And you can see there is a selective accumulation of the particles in the tumor once you have the folate functionalization. So this can make more target specific. And this is another example where not just one agent can be loaded, you can also encapsulate another chemotherapeutic drug together. So that means 2 drugs or 2 drug combination can also be co-loaded together into these nanoparticles. And finally, this is just give me another 1 minute. So this is like another example where we can use these particles for treating blood clots. So you can conjugate these nanoparticles with the help of tissue plasminogen activator, and this tissue plasminogen activator can actually bind the fibrin which is present on the blood clot, and you can also image the how the lysis can happen in situ, and this is how this can also be useful in treating ischemic stroke. So this has a lot of applications in other diseases as well. So overall, my conclusion will be like these nanoparticle platforms are very interesting, and there is a lot of versatility in terms of its optical properties, high stability, storage and all. And most important is that it can be fabricated autologously, or like how you typically store blood in the bank. The same way that engineered RBCs can also be stored, and whenever a patient is needing to be treated, those can be injected accordingly. and it can be useful as a carrier for diagnostics, as a carrier for genetic materials, carrier for therapeutics, and also as a pathology agent for different kinds of particles as well. So these are, I thank all my collaborators, there are some national and international collaborators, along with some of them I work with them within IIT as well, and also I thank the funding agencies, and last, this is my team. Thank you so much for listening.
Thank you so much. I think we can have one question. Any question? One question.
Yes. Yes. I mean, the extrusion. The extrusion can be controlled. So we have, there are different types of membranes which are normally used. Like this is a sequential extrusion process. If I have a micro-sized particle, I can directly bring that micro-sized particle to 100 nanometer. I have to do it sequentially. So I have to put a 800 nanometer membrane and first bring that to, like, let's say 1 micron. So typically a human blood vessel is 4 to 5 micron. And from 4 to 5 micron, I can first bring it to 1 micron. And from 1 micron, I have to bring it to 400 nanometer and then to 200 nanometer. So this is a sequential process. Yes. And we can separate them based on density gradient segregation.
Thank you so much, Dr. Ravaraj, for your presentation. And we will move to the third invited speaker.
On behalf of our organizing committee, I request once again both the moderators to give a moment to Raviraj. And by the way, Raviraj is the organizer. We can give a big round of applause.
Thank you.
Now I request Professor Khalifa Al-Sakari, the head of the department of Civil and Architecture Engineering, to introduce Dr. Ashish, who is the next invited speaker from Biological Science Instruments.
I would like to welcome Dr. Ashish for the third presentation. Dr. Ashish will deal with force control using EWE and ECC control mode, monitoring half-set voltages, EWE and ECC, and the full-set voltage simultaneously. I'll give a brief introduction about Dr. Ashish. Dr. Ashish received his doctoral degree in physical sciences from CII National Institute for Interdisciplinary Science and Technology in the year 2018. Post-completion of his doctoral degree, he did his postdoctoral studies in the Department of Physics, IIT Madras, for a year. Later worked as a research fellow in the CEL, a supercapacitor manufacturer. His research interests include the development of high composites as torus for various energy storage devices like supercapacitors, lithium-ion batteries. He is working as an application scientist in bioelectric. His nature of the work is related to application support in the field of electromechanical workstations. So I would like to welcome Dr. Ashish for this presentation.
Thank you, Professor, for
So the previous two talks, we have seen how nanomaterials can be used in wide range of applications. So in the next 20+ minutes, I will tell you how equally important is the testing systems related to applications related to electrochemistry, like lithium batteries, or also like plastics. So we have with us Mr. Dr. Kumar, who takes care of the sales and marketing activities of biology in this region. So before going into the technical session, I will give you a brief introduction to what we manufacture. So we support academic research as well as industries related to R&D in wide range of applications like energy storage and conversion, material characterization, corrosion related activities, sensors, some rapid analytics and spectroscopy which is related to biological activities, and fundamental biological chemistry. So we have 5 different products, like the first one is potential tests, galvanometer tests. So as I said in the first, we can talk about more about nanomaterials materials, where we can see we can use a simple paper-based systems as flexible substrates for different types of energy storage devices like capacitors or batteries. So in using a simple potential test or galvanometer test, we can functionalize it, we can characterize different types of using different techniques like water-training, water-training, and advanced applications like galvanometer. So using these techniques like potential tests, we can use different techniques associated with this to related applications like in different means of electrochemistry. So we have a dedicated battery testing unit where we can test the battery cycling process, which is called as BD lab. So we have material characterization products, which we can do characterization of materials in different group temperatures. So in order to have like a localized electrophysics studies, we have scanning electrochemical dosation, which is called as a scan lab product. And we have something related to biological samples like cellular hypertension. So that is a CD lab. So with this introduction, I'm coming to the technical details of the talk, where I'm mainly talking about 2 different topics. One is how to control or how to simultaneously measure the half cell as well as full cell of a lithium ion battery. And one more topic is that how reliably we can do an electrochemical evidence spectroscopy using a parameter called as quality indicators. So this is just an introduction on the outline of the presentation. So normally what we do, we try to study, for example, lithium battery into an ecosystem where we measure the whole cell voltage. So if you want to understand like how each like a typical electrode and an annual electrode is contributing to the cell performance, we need to have an understanding. We usually have created a half cell and then with respect to the lithium method, and we try to study. So if we have a system where we can measure the half cell as well as full cell simultaneously, it will be a very huge time-saving process. So I think this is one such potential step where we can control the working electrode as well as common electrode simultaneously, and we can measure the half cell and full cell. So electrochemical impedance, again, it can be used in wide variety of applications, like in order to understand different types of resistance, the kind of diffusion process, we will be using electrochemical impedance spectroscopy. So how we can have a very good electrochemical impedance spectroscopy using this potential test, using the parameter quality indicators. So when we say potential test, we will be having a lot of connection leads that is coming on the potential test in the form of cables. So we have the 2, 3, 4 as a specified terminal leads where we can say that normally we use to work in the working electrode, reference electrode, and as well as common electrode. So we have a separate power and sales cables for the working electrode. We have a separate power and sales cable for the common electrode as well. So we will be having the working electrode, the common electrode, as well as the reference electrode. So these are the cables that will be coming out from the potential test. So what is the importance of doing different types of electrode systems? Normally we do, as I said, in a double electrode system, we measure the whole cell voltage. So with respect to, if we have a reference electrode, we will be having a third electrode coming into the picture, we will be going to the electrode system. So we also have a system where we can do a 4 electrode or 4-point measurement, where we can have a very good, we can reduce the equivalent series resistance that is coming out from the potential
potential that cables and connectors. So this is just an advantage of using 2, 3 as well as 4 electrode systems. So just I will point out how important is the 4-point measurement compared to the 2-point measurement. So this is just an example. You can consider this R1 and R3 as a potential state cable, and if you want to study the response of the cell R2, if you are doing it in a 2-electrode system. For example, if you are doing it in a potential static mode, so the response of the cell will be as a whole R1 plus R2 plus R3. All the resistance will be getting together. So we remove this power sense cable, and if we connect the sense cable directly to the cell, we will be able to monitor the exact changes or the exact impedance changes that is happening to your cell electrode. So this is just an impedance microscopy of the 90 slot where you can see that this is the 4-point measurement, the red one, and this is your 2-point measurement. That is the 2 milliohm changes that is happening when we do it using a 4-point measurement. So how again we are able to monitor the changes happening within your cell. So that is the advantage of using the 4-point measurement compared with the 2-electrode measurement. So we have different types of potential tags, like the technical details are, you can have the discussion as well, we have solid and outside of the wall, we will have the discussion over there. So we are having basically 2 different technologies, VMPP and MPP. So this is normally what we do is that we try to record or try to control the potential between the working and reference electrode. We try to record the current between the working and counter electrode. So that is the standard condition. So if you want to record, as I said, if you want to record this half cell as well as the full cell simultaneously, just what you have to do is that you need to control the potential between the working and counter instead of working and reference electrodes. So just you want to swap your potential stack cables in such a way that we will be able to monitor the exact changes happening in the half cell as well as the full cell. So this is the standard connection mode where we want to just swap the cables, and so that we will be able to monitor the half cell as well as the full cell. So this is just an experimental evidence to show we have done it in a 3-electrode system using a simple sodium chloride solution. We have used the platinum as the working and the counter electrode. So here is the green one is the working electrode changes, the red one is the counter electrode, and your blue one is the full cell changes that is happening to the system. So this was recorded in a very simple potential stack using a 3-electrode system. So when it comes to battery cycling with respect to a reference electrode, we need to have a separate setup like a switched off T kind of cell where we can introduce this reference electrode and we will be able to monitor the exact changes happening with respect to each electrode. So normally what we have a cathode based on NMC, we have a graphite anode, so we will be having electrolyte systems. So if we have a setup kind of this, for example, if you want to control the full cell between the graphite and NMC, we can have this connections over here. So we can also monitor the changes with what is happening with respect to cathode. With the lithium metal, you can have the connection. For example, if you want to know what is happening at the anode side or the graphite side with respect to lithium metal, we will be having this connection leads. So using this setup, we can cycle the battery with respect to the reference electrode. So this is what just I want to show. This is the working electrode potential, this is the counter electrode, and you can also monitor the full cell using like how we get a full electrode system. So this is the potential stack comes with a very powerful software and as easy lab. We have 95% of electrode chemistry technique. So this is just an parameter settings window where you have to pick. So normally what we do, we get the E-cell response. If you want to record the half cell, just you want to click the common electrode potential. And there are a lot of galvanostatic methods like galvanostatic cycling potential integration or GAT or GAT expressions can be used. So there are different techniques or application oriented techniques associated with this EV lab. So this is just an example where we have done it for the battery cycling with respect to the reference electrode. Where you can see that this is the response of the graphite anode. So this is the response of the cathode, and this is the full cell measurement. So with testing systems and an appropriate cell, we will be able to monitor the changes happening like with respect to battery cycling with respect to the reference electrode. So this is all the simultaneous measurement. So I would like to come to this point where we measure electrochemical impedance spectroscopy in different applications, where we will be getting different types of parameters like electrochemical, like solution resistance, or charge and resistance, or different kind of diffusion process. So this is just a really where we have science and equipment in form of potential voltage, and we get a current that is called as potential static areas. If we otherwise like we have current giving us an input amplitude, and we try to measure voltage, that is a gap number control and electrochemical. So basically, is that we need to have a linear system. The system should be like invariant. So it should not, the parameters defining the system should not vary with respect to time. So this is the exact condition where we can do an electrochemical impedance spectroscopy. So basically, we are all working in electrochemistry, where we can think of materials undergoing oxidation and reduction. So it is a typical non-linear system. So what we do is that we consider a part of this non-linear system, we apply a very small science amplitude, and we consider it as a linear system. So that is how we are giving science input amplitude. So this is the linear stationarity is the main concept behind this electrochemical impedance spectroscopy. So as I said, linear time invariant systems, like it is defined, the simple RC circuit, parallel circuit is a best example, and as analytical parameters define capacitance and resistance chain, it will be different time invariant system. So what if a non-linear time invariant system, like a lot of electrochemistry based applications are coming into the picture? So in addition to the fundamental frequency, there are a lot of harmonics of frequency coming out from this non-linear system. So how do we define? How do we take the input amplitude? How do we know that the input amplitude that we give to the system is right or wrong? So that is what I am going to try to explain in the next few slides. So this is, as I said, using the parametric orders, EAS qualitative indicators, we define these systems. The proposal harmonic distortion, which initially gives a linearity of the system. Non-stationary distortion is like the response of the system should not change with respect to time. It should be a steady state. So that is one non-stationary distortion. Non-stationary ratio is something that means the accuracy of the system or the accuracy of the protection access. So again, the discipline where we know like this is total harmonic distortion, which means the linearity of system. Like it is basically quantifying the fundamental frequency that the harmonic. So similarly, we have for non-stationary distortion. So like in addition to the fundamental frequency, some adjustment like top frequency will pop out in the area of frequency range. So this is the signal noise signal ratio, which basically defines your accuracy of the system. If your system is high accuracy, you will be able to monitor the exact impedance just happening in the system. So how do we interpret them? So we have kept some benchmark values, like for example, if you total harmonic distortion, if you want to define the linearity of the system with total harmonic distortion. So if it processes it like beyond 5%, we should know that it is going with the non-linear spectrum. So you need to have a benchmark where you have to set the impedance like below 5%. So that is how we use this for indicators as a parameter to define a very good impedance data. So we have tried using a very simple resistor and capacitor component. We try to study different systems. So this is a typical example of linear systems. So linear systems we don't have confusion. It is perfect. So for example, we have done it in increasing amplitudes like 2, 5, and 2, 20. So this is the organized for the impedance spectrum. So we have used the total harmonic distortion parameter. It well comes with the below 5% ratio. So the system, if it is linear, it is fine and perfect. But when it comes to non-linear systems or time invariant systems, so we have to use this parameter called as total harmonic distortion in identifying the right amplitude. So you can see that if this is the response like of an IV curve, we try to do somewhere over here in impedance spectroscopy at different increasing amplitudes.
So here also we have done it at different rates like 2, 5, 10, 13, 15 and 20 millivolt. So this is the response of that particular impedance plot. So at one stretch we may see that whatever the amplitude we are getting a very good semicircle, we may go forward. But this is not the case. So it is like any one of the amplitude is the perfect one. So other thing, the impedance data will be not the right one.
You have 2 minutes, please.
So using this quality indicators, we can see that the 2 and 5 volt amplitude is coming well below this 5% reject using the DHD parameter. So rest all things going to the nonlinear region where we can see that the impedance data is not accurate. So you can use 2 and 5 millivolt, that is the perfect amplitude that you can apply to the system. So this is just again the settings of a potential controlled impedance spectroscopy where we'll be having the rest time like open circuit voltage, the frequency region or the sinus amplitude which we can apply over there. So this is again an advanced safety settings where you have to tick mark this EIS quality indicators before you record an electrochemical impedance data. So in short, like if your THD is too high, you need to decrease your excitation amplitude. If your NSR is too high, you have to play again increasing your amplitude with excitation. If you are working on some systems like lithium and batteries or corrosion related thing, you have to wait for a more period of time to have a stable OCD, or you should make sure that there is not much drift in the open circuit potential of your systems. So this is how the NSD parameter, we have to wait for a longer period of time. This is the sinus amplitude which we apply to the systems. So one last topic, like there are 2 different topics like potential control or a Galvano control systems. So potential, normally we use a potential control system for operating any of your systems. So when it comes to Galvano control, for example, you can think of a very low impedance system like lithium and batteries. So this is just an example where we can see that this is the red triangles are with respect to the internal resistance changes happening with respect to OCD. Okay? If we try to record an impedance in this particular region, we will not be able to monitor the exact changes happening in the resistance. So if you try to record exactly the changes happening to the system, we have to do a Galvano controlled electrochemical impedance spectroscopy. Similar is the case with the corrosion. The parameters define the system will change as a function of that. So there you can use a Galvano controlled electrochemical impedance spectroscopy. So basically, when you do these systems, especially the low frequency, you get a lot of diffusion of processes. So what happens is that it takes a huge time in doing such experiments when we go, for example, 1 megahertz or 7 megahertz region. So what we advise the researchers is that you can split your the frequency variability like 2 or 3 segments, then you can try to use spectrum variability and end up saving a lot of time. For example, if you try to do it as a single segment, it will take almost 35 minutes, and if you try to record by splitting into segments, you'll be able to monitor the exact changes that morning. You can monitor it by 10 minutes. So that's how you can split your frequency variances, and you can save time using different segments. So this is just an example. There are a lot of things where we having there's not much change in the record spectrum, but you have time saving process. So in summary, we have seen how we can use the potential add to measure the harness and usage of energy storage devices, and how we can use the parametric quality indicators for related to electrochemical measurement. So with this, I thank you for your patience. You can always visit this website where we will be having a lot of learning sessions, technical notes and application notes in the overall topics. So thank you all once again for your patience. Now we have our website for more product related information.
Thank you, Dr. Ashish, for your presentation. Any other questions?
very good Indian system. So here we are seeing an increased. So this is very basic. Here you see the mass that in emergency increases. So any that increasing is what the basic meaning as and number two. So how can we lifetime expectation of the media by measurement of the
First one related to process, it depends on the material which you use. Maybe different materials have different resistance. It will work on some interfaces like interfaces or efficient is able to communicate. So based on that, the charge and resistance will be in a very high senses and responses. So that this is like an interface like where you can already materials like how efficiently ions are able to move between the interfaces.
I'm asking that the diameter of the semi-circle showing
so they can have like more efficient the diffusion should be happening. So that's why this is like the resistance will be low. So based on the diameter of the semi-circle we will be able to define charge and resistance. So that's what it depends on the material, like how efficiently it is able to move. Like we talk about and energy storage devices, like how efficiently the atoms are able to move from anode to cathode during charge and resistance process. So based on that concept, we can define the charge and resistance.
Thank you so much for your comments.
Life expectancy, for example, like for lithium battery, we will be able to do the battery cycling. For example, we don't want to do 500 or 600 cycles, which is really like a process. We are having a feature where we, like by our just 300 cycles, we will be able to use some mathematical models to define how efficient or how we the performance.
But any formulations there, how to calculate what would be the life of the material?
For lithium devices, you are having the physical model, like you are using second order polynomial to determine the characteristics of the pattern. So this is software that we are providing.
Okay, thank you, Dr. Ashish, for your presentation. Thank you so much.
I now request the moderators to present the memo to Dr. Ashish on biological science. We have keynote lecture now by Professor Sadasivuni belongs to the Department of Energy, Science and Engineering, DGIST, South Korea. He will be talking on fuel cells energy. I request Professor Khalifa sir to just introduce this keynote speaker to the audience.
I would like to welcome Professor Sangrat Shan Moga from the Department of Energy and Energy Science and Engineering from the Institute of Digo in South Korea. And this presentation will address the fuel cells energy. Just I will give a brief introduction about Professor Sankaraju, and he obtained his doctorate in 2004 from the Indian Institute Department of Chemistry, Parana University, Israel, as postdoctoral fellow. And in 2011, he was appointed as an assistant professor at DGIST and promoted to a tenure professor in 2019. Professor Shan Magam currently has 138 referee publications and 5 Indian patents and 5 12 Korean patents. I would like Dr.
Thank you, Chairman, for the kind introduction. And it's my pleasure to be here in Vietnam. This is my second visit. I was there in the previous conference organized by Sarasandra Babu. And I want to thank the organizer, particularly Dr. Kishore, for inviting me here today. And today I'm going to discuss about electrocatalysis for sustainable carbon-free fuels. So the title itself, you can understand, we have to look at alternative fuels to fossil fuels. Which means that now if you produce electricity from fossil fuels, you are producing carbon dioxide. So which is one of the greenhouse gases. So which is not what we want. So before that I want to thank my students, particularly I'm going to discuss about the work carried out by Twitter on NOR. And also at the later part I will discuss about Hamdan, which is a technical student. And he came from Secretary correctly. And he joined the PhD postdoctoral researcher, came from ISR Kolkata. And also I want to thank funding support from NRF. I have some projects from 2014 until today. So we are working on ammonia synthesis using NOx. So how to transform NOx to ammonia, that is very interesting. And also I want to thank the industries, in particular like Hyundai Motors, next generation vehicle, and also the custom materials. So before I want to briefly introduce about where I come from. So this is the campus of DGIST, and DGIST is one of the K-star universities. In Korea we have 4 IST universities. The first one is located in Daejeon, in KAIST, and the second one is this in Gwangju, and University in Ulsan, and the next one is DGIST, which is similar with IITs in India, right? Or ISR. So let me tell about some history about DGIST. So which is founded as a research institute in 2004, and subsequently, we need students to run the university. So what we did now, after 4 years, we amended as an education function. So we accepted students in 2011. First we accepted masters, PhD. But in India, what we do, we accept undergraduates without having to study or whatever. So that's the Indian system. The Korean system, we have a perfect campus here, like research institute, and we accepted students. So meanwhile, I moved from Japan to Korea, and they built this campus, graduate school. We have 5 different campuses. This is energy science engineering, robotics engineering, and brain science, and IT, and material science. So we have central library, and complementary to the graduate school, we also have institutes, like exactly the same research institutes are located here. So we do research between graduate school and like institutes. So after 4 years, one of my students, the first student graduated from my lab. He is the faculty in Thailand. So Dr. Sadasivuni Ashok Kumar is assistant professor and deputy dean at King Mongoose University. So I'm really very happy that he is a first student from 3 years and become faculty. So after say 2014, we accepted undergraduates because we need students to run the university. So we train the undergraduate students, we teach them, and try to take them as master students or PhD students. So that's the goal. And so today I will be discussing about my topic on electrocampus development. So first I will just briefly about what is necessary, and I'm going to discuss about 2 examples. One is electrochemical transformation of NOx, or say nitric oxide to ammonia, and next one is about anode catalyst or water oxidation. So with that, we have to look alternative fuels. So it's very important. So by looking at those two chemicals, this is carbon-free fuels. So when you take ammonia as a fuel and you try to oxidize ammonia, you are producing nitrogen and electricity. The similar with the hydrogen. So most probably the sustainable green fuels are important. And with that, I want to move on to the second topic, which is about the flow batteries for power sector. So hybrid membranes for flow batteries, I will touch upon this, and with that, I will summarize my talk. So when you're looking at the current scenario, the human client facing a trilemma, which means that we are obviously, as you see here, the population is steadily increasing, right, as we move on. So which means that now we are exhausting the energy. Not only that, what we see here now, the population is increasing because we are increasing use of the electricity. So what we do now, we are emitting huge amount of greenhouse gases, like the carbon dioxide or SOx or NOx. So it means that now, because of this, so what we experience is that the global warming, right? So what we see here, this is the temperature, right? The global warming related to, say, 1850 to 1900. The temperature is slowly increasing. The reason you see that now we are expecting a steady increase of temperature, which means that how to maintain the temperature less than 1.5. That is very important. So what we can do now, we have to look carbon-free fuels. So people also looking at exploring carbon dioxide as a source to produce methane or higher carbons. But again, it's going to be the carbon-based systems, right, like fossil fuels. So what we thought about, how can we explore carbon-free fuels like ammonia or hydrogen will be the future fuels. So the idea is that a sustainable energy cycle, so we want to explore like renewables, like solar or nuclear, and you can produce the electricity and store them by capturing electrons. And once we know that, you store them in batteries and use it for like applications through the transport sector, and obviously you can use it, right? So also we think about the alternative ways is that how about producing directly hydrogen from renewables? The power produced from renewables, then you have hydrogen is produced that can be stored in using electrolytes or liquid hydrogen using a tank or pipes. So once we have the mature technology, and you can transport to a device which is a fuel cell. So hydrogen is used as a fuel, and you can oxidize and produce electricity using a fuel cell. So where we have the photosynthesis byproduct, and you can use the electricity using the fuel cell. But also you can think about how about directly can we produce ammonia from using renewables? So it's possible. So what we can do now, using some system, electrocatalytic way, you can produce ammonia, either gas or liquid, and you can transport this ammonia to the end user, or we can also use as a fuel to produce electricity by using ammonia fuel cell. And obviously, you can have the end user, and obviously what we see here, you're going to produce only water and nitrogen. So that can be again circulated to the, so we have a systematic circular economy. At the same time, this can be sustainable. So this is very interesting. So when we have this kind of strategy, but we have to understand fundamentals of chemistry. So here we have three important cycles say we are facing how to transform nitrogen to ammonia or ammonia to hydrogen by using oxidation or reduction reaction. But also we have water cycle. So water is plenty, renewable. This can be oxidized to O2, hydrogen, at room temperature using a catalyst. In a fuel cell, what we do now is supply hydrogen and produce electricity. But also now we are thinking about, say, we have carbon dioxide. Somehow we are depending on fossil fuel-based power sector, like coal power plants or cement-based industries. You are emitting a huge amount of carbon dioxide. So you capture the carbon dioxide and transform into value-added chemicals like methane or C2, C3-based chemicals. So we have methane. But methane can also be fed into a fuel cell using solid oxygen fuel cell at temperature, and you can produce electricity, right? So we have three important cycles. But looking at those reactions, we need to understand the properties of the material. So what we look at here, the structure of the catalyst, or understanding the size, active site, and thereby you can increase activity and stability. So you may have some kind of understanding the atomic levels of the materials. So thereby you can look at the structure, functional relationships, and eventually you can explore them in applied research like devices, right? So our idea is that how to couple the electricity which is produced from renewables. Like we have in wind sector, wind power or solar. So we produce electricity from here, which is renewable, and integrate with electrolyzer. So what we have here is supply the power and produce hydrogen. So we have water, you can also input nitrogen or hydrogen, then you produce either hydrogen or ammonia, and you can store. So this is an electrolyzer or energy storage system, and once you store, you know how to store those chemicals, and eventually you are going to utilize for end users. So we use a fuel cell energy consumption system, so where you can be stored as a power plant, or you can also use in like automobile industry. So this is what we are thinking about. Production of hydrogen and hydrogen utilization is very important. So this is mostly green as well as sustainable. So this is our idea, which is not possible. And so they say that we want to use ammonia and hydrogen. So what is those two chemicals as energy carriers? Based on they have very high energy density, they can appear volumetric energy density and with respect to energy density. So ammonia has much higher compared to hydrogen. And also looking at the gas weight, which is the topmost high energy density. But the idea is we have to get rid of this one, right? So when we say that the Middle East or some of the oil-rich countries may not be interested, but eventually we have to go from carbon-based system to carbon-free system. That is the goal, so that we can maintain the atmospheric temperature below 1.5. And further, so ammonia can be one of the performance candidates because which has really high hydrogen storage amount, which is about 17.8%, and so looking at other components. But the problem with this process of ammonia production is that which is energy independence, which means that now to produce ammonia by using paper-based process, we need hydrogen, and we have hydrogen in our atmosphere. But this hydrogen is produced from petroleum feedstock by using reforming process. So when you are using reforming, again you are emitting greenhouse gases. So, and not only that, this process needs very high temperature and high pressure. So that's why I get energy intensive and also emit carbon dioxide. So what we do now, we are looking at a kind of sustainable roadmap for ammonia production. So we combine with, say, we have SMR and other processes. I skip this one, but looking at this side, the bringing process is that you produce hydrogen from electrolyzer and use the ammonia electrolyzer. So thereby you can produce ammonia, which is a zero carbon dioxide system. But when you think about ammonia, so how can you produce ammonia? The best process is using nitrogen. But the problem is that nitrogen is a very strong molecule, which has triple bond. So you need to break to make ammonia. So the breaking nitrogen molecules need much higher energy. So we talk about other components, other compounds like nitric oxide. So this is slightly lower. So we have a whole other bond, and then we can oxidize using electrocatalyst, and also which is much lower energy. So we talk about using NO as a source to produce ammonia. And so this is the same system. You can go to the circular economy, ammonia economy. But the problem is that we have NO, nitric oxide, with the water, and use input some energy. You can produce a series of nitrogen compounds. So we are interested mostly in ammonia rather than those compounds. But among this process needs certain potential. So this is about 0.71 volt with respect to the difference of level. So how to produce selectively this lower those compounds is also very important. Let me show you some examples of what we did in my book with that. So we have prepared several catalysts from say 2015 or 2014, and if you are interested in those papers, but recently we are interested in ammonia, so those papers, this is a review, invited review from experience analysis, and also some more of this one, and I'll let you have interest. So our idea is to prepare a catalyst by using condensate. So what we did now, we take a simple compound, which is procedure another, where we have nickel. So this compound has inorganic cyanide group. So you take this complex and try to heat up, otherwise. So what will be here now, you get a core of metal, and at the same time, the carbon will solidify, forming a kind of positive particle, and we try to control the temperature, so we can be able to show the particle size as well as the carbon. And from here, you can see that now we have a high crystalline nickel in the core, and it is surrounded by a thin, like about 5 nanometer thick shell, alright? So now we use this as a cathode and try to convert NO. So by using this kind of hydrogen cell, so where we have here the cathode line, where we have NOH first and try to reduce on the cathode. And at the anode side, what we have here, we have water. So water can be oxidized on a cathode again. So you can produce the ammonia, right? So this is some technical analysis of this one. At the same time, we have with several materials like nanoparticles, on oxide, and metal, carbon. So what we have here, we have nickel particle as a whole surrounded carbon. There is a strong interaction between metal to the carbon that influences the chemicality. So here we try to calculate the ammonia heat with respect to the state. So what we found that we have three types of catalysts. One is nickel and one by changing the temperature, and then the shell thickness also. So I don't go into details, but eventually when you have nickel core with NC, that catalyst has highest activity for synthesis, and then we also try to look at the durability of catalyst and can enable around say about still really aluminum. And also we demonstrate that so this is a small scale solar panel, gallium nitride. And when you expose this solar panel to a typical lamp that can break electricity, like say 1.5 volts, whatever. So that is connected to the electrolyzer where we have cathode line, which is nitrogen exposed here, and we have water, so cathode is here, and from here we calculate the solar fuel efficiency is about 7%, quite low, but this is a demonstration. First time we demonstrated. But eventually you see that the yield of ammonia is quite high, and the details can come here. And so further, this is a system in liquid phase. We have electrolyzer, we have cathode, but that is not implementable in industry. So what we do now, we use polymer-based electrolyzer. So to do that, we try to prepare single atom catalysts. So earlier, we have particles. So the particle consisting of several atoms. But now we want to make a single atom, which is less than, say, 1 nanometer, by using some strategy. So we have iron with the polypyrrole nanofibers are infused and introduce second metal in order to control the selectivity of ammonia synthesis. And eventually we pyrolyze. And what we have here, you have the single atoms are embedded in the carbon tubes. So that can be seen from here, maybe you have the tubular structure, but looking at this one, you see that we have a small dot, so that is less than, I would say, this is 5 nanometer, so we have less than 1 nanometer. So this is a kind of dual elements. You have nickel along with iron. And so we also characterize using XPS and other things. I want to just tell about, we have the total metal content, which is about less than 0.58%. So the amount of metal cannot be detected in XRE, so we have mostly amorphous nature, so we have only carbon being right. And so further, we use this catalyst and implement it in a real scale electrolyzer, so where we have a polymer membrane. So with all membrane electrode assembly, so where we have anode, cathode are separated by a polymer membrane. So at the anode side, we pump water, aqueous water, so water can be oxidized and produce oxygen. At the same time, protons move from anode to the cathode because we need the protons to produce ammonia. But at the cathode side, we something like gaseous NO, not dissolved NO. So now we have NO along with argon. So this is pumped using a amplifier, and NO is reducing on a cathode surface here and forming product is ammonia. So ammonia is dissolved or trapped in a trap, and that can be monitored or quantified using various spectroscopy. So we have used like calorimetry and also NMR to confirm the product as well as quantify. And this is the components of the electrolyzer. This is small cell electrolyzer. This is the MEA I was talking about. We have the pump which circulates analyte water along with the assay, and we have the cathode side. So those are the components. We have the carbon flow field, and we have the polymer membranes coated with the cathode catalyst and the catalyst are over here. So what we did now, once we make the electrolyzer, we try to understand how our catalyst can be able to produce ammonia. This is the typical applied cell voltage, and with respect to current. Then obviously, if you can bring down the voltage, then the system has highest efficiency. So now once we have iron nickel, cathode side catalyst, and thallium oxide anode, so this system has the lowest potential. So it means that which has highest activity. So that can be seen from here. So we try to look at how much ammonia is produced during the electrolyzer, and we monitor the ammonia using indophenol blue method at a given wavelength. You can check the quantify. So at 1.1, when we run the electrolyzer, you see that this is the yellowish green, so it means that ammonia is much lower. And as the color is increasing, so we may have more ammonia. So that is quantified and plotted here. So the iron nickel dual single atom catalyst shows the highest ammonia in it, as well as the highest efficiency, and that can be looked at here. So I can skip this one. Not only that, our system can operate quite long time. So this is a typical current density with respect to time, and here the blue one is the current chronometry at 1.5. So this is the current density. It can show and maintain the same current. At the same time, it can also show stable efficiency, right? So which is about 85% in a single cell electrolyzer. And this is quite interesting. And with that, I want to move on to the another topic, which is about water electrolyzer. So where we want to explore this work was done earlier. So first, I showed the latest results. So this is about the same story. We have the cobalt core. This is like avocado. You have avocado, right? So India is also is available. You have a metal is protected by a shell, avocado shell, right? So this shell is again a carbon containing heteroatoms, like nitrogen atoms are embedded. So we used in anode side for water splitting. So this is a typical cartoon where we have a cobalt. So cobalt color is given here, and this white minus is reacting on the surface and producing O2 gases. So we use as anode catalyst. And one of my PhD students tried to develop a catalyst based on Prussian blue. Now here we have two metals. One is cobalt along with iron, and we try to change different metals in order to understand the selectivity and other issues. I can skip this most the details, and we try to parallelize, and we have a similar core of two metals. This is not single atom. This is a particle, small particle, and try to characterize using XRD. Maybe I can skip this one. So by looking at the microscope, so what you can see here, you have the low magnification EM images, but high resolution, you see that this is a beautiful core, highly crystalline, and the core shell is about say less than 5 nanometers. For this is the cobalt iron. So the cobalt iron is uniformly distributed within the core. That can be seen from here. The blue color represents cobalt, and the green represents iron. So you have a particle which contains both metals, right? So similarly, we vary nickel iron, nickel cobalt. So we have exactly the same type of structures, core with the shell, right? So we try to explore in liquid-based electrolyzers based on noble metals, uranium oxide, anode, and platinum cathode, and also the rotating catalyst. You can see that if you don't have any catalyst, which is much higher cell voltage, or I would say 1.9, but once we have cobalt along with other metals, so you can bring from here to here. So if this is much better. And not only that, but looking at this year, our catalyst can able to oxidize water, produce hydrogen, oxygen continuously by connecting the solar panel. So that was we demonstrated. So you see that the backdrop, you have solar panel, and electricity produced from this and connecting with this electrolyzer, and we can demonstrate that this electrolyzer can able to operate without any change of the cell voltage about 760 amps. The loss of cell voltage is negligible, less than 5%, right? So we said now this can be adapted by the industry. So what we do now, we can consider a large-scale solar plant which can produce electricity during daytime, and that can be stored by a battery, and during night time you can produce hydrogen. So this would be very interesting for Indian say scenario where we have not integrated, but we want like gas stations where we have electrolyzer that can produce hydrogen using solar panel, and hydrogen can be used subsequently during night time to produce electricity using a fuel cell. So this is quite interesting, but we are looking some industry partner. So anyway, that's the story. And I want to move on to the last topic about the hybrid membranes for high efficiency zinc bromine redox on flowless battery. But I think I can skip this one. I will talk about only flow battery. And we know that flow battery is mostly applicable for large scale power sector. Right? Also, this can be applicable for charging station. We are talking about EV, right? The future is EV, next 5 to 10 years. So you need a charging station. So this would be very interesting for charging stations because we have here a chemical-based system. We have alkaline. This is based on aluminium and alkaline. So when you try to circle substituting alkaline and try to generate electricity. So obviously this can use some, say, some 50 more kilogram, but actually this is very high. But the problem with when you're flow battery is that the solubility is not quite high. So the efficiency is based on the volume of the container and the concentration. So we said now we are moving from flow battery to zinc based on the electricity as well as solubility. So the zinc, you know that this is quite cost effective compared to the vanadium. And not only that, the catalyte is based on bromine. So bromine, sulfur, iodine is much cheaper. So we can consider. And not only that, the actual energy of bromine system is that double than the vanadium. So this is quite interesting. And not only that, there is solubility of zinc, so it is quite high. So if you have high solubility, so the energy is based on the chemical compound, the concentration, and the opportunity is based on how big the system you have. Right? So this is one. So when you look at the flow battery, particularly zinc bromine, you have zinc. This is very similar to the battery, because of the battery. So you have the red formation, but I don't want to concentrate on this one. We are interested in the catalyte. So catalyte you have bromine. So the main issue is that the crossover of catalyte from here to here. So we need a separator. Polymer separator. I mentioned that. So now that okay, so looking at some chemistry in the catalyte, we have formation of polymer, react with those reactions, and we need separators. I'm going to minimize moving from catalyte and analyte. If there is a movement, then the battery may not prolong. So we can do that. Somebody now, there are processes separations like dynamic from Japan, characteristic from Japan, this is porous in nature, and you have also couple of nitrogen membranes like vanadium, so the dynamic only cations, not anions, but we need ionic transport. So now I said that we can try to develop a separator using a nano additives. So nano additives are based on silicon. So intuitively, based on our experience, what we did now, we have a silicon nanoparticle and we try to modify using silicon, like a small molecule, and then we anchor like those sides. So we have here silicon. You know that silicon can be condensed on silicon surface, and we also have cations and anions. So now we have this one, the silicon surface is modified, so which has dual mobile sites. One is quaternary ammonium cation, another one is sulfuric acid. So we use this as a nano additive and prepare the separator based on Nafion. So we also try to understand the bromine capture property of this additive using this test, and we can see from here the pure silica are without blank, right? So you see that this peak means you have bromine is present. But once we have the additive, which has some functional groups, this functional group can capture bromine, a complex bromine. So this peak is completely disappeared. So which is quite interesting to us, right? So what we did now, we also confirm this property using XPS. So you see that now we have Br2, all the bromines are absorbed on the surface of powder, okay? And further, we also check the physicochemical properties. I can skip this one. And not only that, we take this additive, introduced to the polymer. So we prepare the polymers. This is a Nafion, commercial Nafion, and this is our membrane. So before is a transparent. But once you add a bromine, take this polymer, dip in zinc bromide. So if bromine is captured in the polymer surface, you see that the color is changed. Which means that now here, no change in the color. This membrane is not able to capture in the bromine, polybromides. But whereas now here, the bromine is uniformly present on the surface. You see the color, right? So also we confirm using Raman. So those peaks comes from here, and this black comes from here. So it means that you don't have any peaks at all, right? But also we check the ion connectivity with respect to time. So once you absorb bromine, polybromides on the surface, the ionic conductivity will decrease. So we try to understand how this can retain. So we see that there is a about 50% loss of the ionic conductivity because we have a lot of bromines are absorbed. So we need to optimize. So subsequently we check the battery performance with the different separators. Like we have a commercial, and we also have a membrane. So obviously the red one is what we wanted with like a zwitterionic membrane where we have two cations, anions, so that can capture. And so we have very high polemic efficiency, but also inhibition is very important. So you see that now from here, this membrane has about 88%, right? Further, we also look at the rate capability. Maybe I think you all know this one. I can skip this one. And so we have further that we try to look at how this battery can run in a long term. So this is energy efficiency, and with respect to cycle number, so our membrane shows about 550 cycles can be operable. And how this additive can suppress the bromine crossover from cathode to aniline, and we propose a mechanism. We have additive here, and we have a protein channels in the Nafion, and the bromine can pass through along with the zinc, but at the same time, the polymers are complex on the surface of silicon. So thereby, you can affect on moving from cathode to the aniline. So you can extend the graph cycle. Okay, so why we explore? So today, I noticed that by understanding the surface of catalysts, you can be able to improving the efficiency of the processes. Either way, I was talking about water to O2 or hydrogen. At the same time, today I talk about N2 ammonia, but I talk about NO2 ammonia. And so, later on we also discuss about how we improve stability by using some strategy, protecting campus surface from leaching during the database by having a campus surface so that we can extend the durability. And eventually, so today we discuss about the approaches like which are anticipated to contribute to the development of sustainable technologies for penetration in the global market. So with that, I want to thank you for your kind assistance. And this is the campus, and we have I think the small pieces of campus. And if you have any chance, you're visiting Korea, so please let me know. I will be happy to host. Thank you.
Thank you so much, Professor Sadasivuni, for your presentation. I think we can have one question. Before lunch, I am sure you are angry. So what question do you have?
It was very nice presentation, impressive. I have a question related to this ammonia economy. It seems to be a very odd approach. of criticizing it. Because once you have ammonia, it produces NO2, which is not usable at all, and 3 not consumed as well. So it's better, it cannot be better than even carbon economy. So what is the philosophy of thinking behind this ammonia economy?
Yeah, that's a good point. See, this is the concept. We need to look at innovative concepts. You understand? But eventually, the idea of taking from lab to industry, we need to go a long way. So approach is that either taking N2 as a starting compound, because N2 is likely, and you need to do this process at 200 rate using electrochemistry, electroanalysis. But now nitrogen to ammonia is done in a process. So this is quite acceptable, right? But you're talking about if you take or if you use N2O and N1, right? The question is maybe ammonia will be oxidized.
If you will, once you use it as a fuel, it will produce oxidized product, which is
That's possible.
So if you want to stop that ammonia synthesis and use it for fertilizers, that's a perfectly that's idea. But moving, pushing towards the fuel production, it will be a big task.
That's true. No, it's say that if you have a better
we have already we are seeing the pollution is going on because snow and are contributing to the smoke.
Possible. Say now people are looking at the CO2 capturing, CO2 methane, the main area, but most of the researchers try to adapt CO. Some people are making CO2, CO4 something, but even ammonia yourself, ammonia is a barrier, and ammonia can be oxidized on a catalyst, and we need to think about selectivity. So I don't want to produce NO, I want to produce completely toxic. So that's quite complicated. It's not possible, but we need to put some strategies, whether my catalyst can be completely, before this story, methanol oxidation, as a fuel cell, people talk about, we use methanol as a fuel cell, but methanol cannot be completely oxidized. You take methanol, which has CH3 OH, because you have to break the CH bond. And so it's completely oxidized methanol to CO2, so it's quite complex. Still CO2 is leaking, but it is not also. You have so many intermediates are leaking on a plastic phase, different phases. So those intermediates strongly bind catalysts, so catalysts will poison. So in case of ammonia, if you have a catalyst, assume that you are a smart guy, you can use a catalyst that can completely oxidize ammonia N2, that's just no problem. But it is not possible. We need to think about it. So that's our job.
Thank you so much. This is an interesting topic, so we can continue this discussion later on. Thank you, Dr.
Thank you, sir. I now request moderators, Professor Sadasivuni and Professor Ashok to present the memo to Professor Ashok Kumar. I thank both moderators, Professor Sadasivuni and Professor for holding this session in a very nice manner. Now it's time for us to break for lunch. I request all the delegates, invite speakers, guests, and faculty members to join for lunch Graces Hall. And I request the students to gather here in the lecture for further discussion. Thank you very much, and we will break for lunch and reassemble here at 2:10.
I'll take the camera to the lunch session.
After this, no break is there, right?
No, there is no break after this. Tea break is there, no? Tea break.
Let's take this. Copy the footage. I might not be there.
to change the battery after 1 hour बैटरी लेने के बाद एक चार्ज
चलो 3 महीने जब तक
Very good afternoon. Welcome to the session 2. For this session, may I request Professor A.V. Hariharan to come on to the dais and act as moderator. Professor A.V. Hariharan. The second moderator of this session, Professor J. Kim. May I request Professor J. Kim to come on to the dais and act as moderator. Ladies and gentlemen, we have 4 talks in this session, 2 keynote speaker address and 2 invited talks. Now I request Professor A.V. Hariharan to preside over the session.
Thank you very much for giving me an opportunity to stay before you and say about the conference, the second session, afternoon session on the lunch break. This session consisting of, as our Venugopal already told, consisting of 4 speakers. And the very first one that Professor Muhammad Al-Abri is going to present. And then the second person who is on the way, we will think of whether to go for the next or something like that. Professor Muhammad Ali Abri. Keynote speaker, Professor Muhammad Ali Abdi, is an associate professor in Petroleum Chemical Engineering Department, College of Engineering at Sultan Qaboos University, Oman. In addition to his academic position, he is the founder and director of Nanotechnology Research Center, SQ2, and he has completed all his tertiary education from University of Nottingham, UK. Muhammad major interest lies in cutting-edge research in nanotechnology, water treatment, hydrogen production, membrane technology, and environmental engineering. He is a member in several national and international committees in the field of water resource management and scientific research. Dr. Ali Abdi has more than 30 major research projects in different areas of water treatment and desalination, nanotechnology for environmental and renewable energy applications, and membrane technology also. He has more than 85 international journal papers and 30 international conferences, 30 technical reports, 4 patents, applications. With this brief information about Professor Muhammad Ali Abdi, I request Muhammad Ali Abdi kindly give his keynote. Thank you.
Thank you, Professor. It's a pleasure to stand in front of you here after lunch. I hope that you had a very delicious one, just like I did. It's an honor to stand in front of all of you here. I'd like to thank Mr. Kishore for the invitation, and of course I would like to thank my very dear friend, Dr. Sadasivuni for being with me on the way. So my name is Muhammad Al-Abdi from Sultan Qaboos University in Oman. And my talk is about advanced wastewater treatment using functionalized membranes. However, I think the more suitable name is treatment of non-conventional wastewater. And I would like to start with telling you, if you will believe me, if I told you that the amount of wastewater from the oil and gas industry in Oman, the amount of that wastewater produced every day is actually higher than all of the water that we use domestically, that is huge for a country like Oman. And this is the part why I'm here to talk about advanced functionalized membrane using any non-conventional wastewater treatment. I will start my talk with introducing the Nanotechnology Research Center that I'm directing, and then looking at introduction to desalination wastewater treatment, followed by emerging contaminants and oil-free water, and then briefly talk about membrane technology and the work that we do on membrane technology for wastewater treatment. So the Nanotechnology Research Center was established in 2017 after it has been a chair. Previously, it was we had a chair in nanotechnology for desalination, chaired by Prof. Joy Doctor, who was a close friend of mine. And we have a state-of-the-art laboratory where we completed so far, actually this is a bit old, we completed more than 25 projects since 2017, and we are currently working on 15 other projects. Our work is divided in the center into 3 programs. We work on water treatment and desalination, the application of nanotechnology on this, application of nanotechnology in oil and gas industry, and the application of nanotechnology in renewable energy, and of course, net carbon zero. So far, since 2017, we have published more than 85 paper publications. We have 4 patents on different parts of the application of nanotechnology. And we are very proud of our capacity building. So we have more students. Of course, we are not as lucky as you. All the order for man is only 3 million, so it's not easy having many postgraduate students. These are some of the highlights that we do in the Nanotechnology Research Center. We do a lot of work on membranes. We have patent on membranes application in water treatment, wastewater treatment. We have another one on membrane distillation for hydrosaline water. Some of the oil-produced water that we have in Oman has a salinity of 4 times the salinity of seawater, higher than 200,000 milligrams per liter of salinity. And we have currently we have a prototype for this, 2 cubic meters per day. We have worked on application of membrane in medical application, catheters, bio disinfection. And we have another also patent on membrane recycling, trying to recycle all of the amount of RO membranes that are used for seawater desalination, trying to apply them for wastewater treatment afterwards instead of throwing them away, which is extremely important because we have a chunk of more than tons of membranes every year that are wasted. We have worked on nanosensors, and we are also working on capacitive deionization, which is specifically used for either industrial wastewater treatment or for brackish water, groundwater desalination. So in general, if we talk about desalination, then you will see that basically the Middle East here are 50% of the total desalination in the world is in the Middle East. And even on all of the world, except maybe here, most of the water that we do and the treatment is for seawater desalination. We do very little wastewater treatment in comparison to desalination, and the same is true for brackish water, groundwater treatment. And this is another statistic which is very interesting because, as you can see here, it was expected that we will be doing a lot of wastewater reuse, beginning very slowly in the 2010s, 2020s, and then we will increase this by a great margin later on. What's very interesting is we see it was expected, this was done in around, I think, 2018. So it was expected that a lot of production of desalination is going to be by concentrated solar power. And there was a lot of talk about this concentrated solar power that it will be the next phase in desalination. However, it didn't really work. And until now, the breakthrough is not there yet for concentrated solar power. Until now, in the Middle East, and I'm sure also in the other areas, we still rely on either conventional power, electricity, from natural gas, or from photovoltaic power, solar energy. So talking about emerging contaminants, of course we are used to in municipal wastewater or domestic wastewater. However, this is only a very small part of the wastewater. We have a lot of industrial wastewater as well. And this is important because industrial wastewater is not one common wastewater like the municipal wastewater. You can say that municipal wastewater is quite conform. It's the same everywhere within a small margin. While industrial wastewater is completely different. We have so many industries, each industry will have its own wastewater. So it's own water, and that's why we really need to think very carefully before introducing any kind of treatment for it. So with this, whenever we talk about wastewater treatment, and it's not a municipal wastewater, the conventional wastewater is not going to work, and we need to think about other technologies and nanotechnology, of course. Enhancement of these technologies using nanotechnology is a very wise thing to do, and it's a wise thing to research on. So what we have is basically, if we look at previous studies, we've seen that there are a lot of microplastics, scapaline, acetylcholine, and salicylic acid in the water. This is in the wastewater. It is also in the wastewater, but it is also found in river water as well. Because it goes from our usage, it moves into the water treatment, but if there is any kind of water treatment, it is not easy to decompose, whether it's chemically or biologically. And therefore, it will run away and it will go into either the sea or it will go into surface water, which will be recycled back to us. And so, and of course, what we do most of the time when we talk about wastewater treatment is very simple. We talk about the product as something in general. This is what we want, the BOD, biological oxygen demand, or chemical oxygen demand. But we don't really look at the specification of it. This is another study from China, where they found that the removal of pharmaceutical and personal care products, some of them didn't even reach 40% removal in the tertiary wastewater treatment plant. So all of that stayed in the treated water and it stayed into the system. It's returned back to the system. So it's very important that we really take good care of this when we talk about wastewater, especially if we are going to repurpose that water for a specific use rather than just throwing it away. And of course, we cannot throw it away because we need that water, we need every single drop of it. Another thing that I would like to share with you is produced water. And previously, we would say that produced water is the water that is produced from the oil industry. And then we said from the oil industry and the gas industry. And recently, we had all of these because, again, it really depends from one area or another. The characterization changes, the properties change. We even have in many wells, in many fields, we have norms naturally occurring radioactive material in that water. And therefore, it's very dangerous. And of course, we cannot really just throw it away. For what we use it for is more than 50% we use it for enhanced oil recovery to produce more oil. And part of it is surface discharge, part of it is for reinjection, and part of it is actually not used at all. And if we compare in Oman, we produce around 300 million cubic meters per day of drinking water from desalination for all of Oman. That's less than 1 million cubic meter per day of drinking water. While we produce more than 1 million cubic meters per day of produced water that we need to find a way to utilize instead of throw away. And this is part of the characterization of the produced water. As you can see, it has everything. It basically has everything. And if we really want to treat it, then we would have to use wastewater treatment, and we combine that also with desalination processes as well. Because there is definitely no one solution for it, not even 2 or 3 solutions are not enough. We need a process with many units, treatment units. This is why we are in the nanotechnology center, we are interested in membrane technology, because membranes are used in so many different areas. They are very versatile. Even with green hydrogen production, it's used for gas separation. For us, we use it for water treatment. And those who are not familiar with membranes, it's a very basic process where it's an area where part of the water will pass through, the other things will not pass through, and what is restricted movement depends on the property of the membrane. It could be because of the pore size and the size of the particles. It could be because of the surface charge, or in case of membrane installation, it is due to the vapor pressure. And for this, the conventional membranes usually are classified in microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. The main used one is reverse osmosis because it is the one that is used for desalination. Nanofiltration is hardly used. The ones that are used for wastewater treatment are either microfiltration or ultrafiltration. And again, the materials also are different. They are versatile. There are many materials used. The main ones are polymers. So the main membranes used are usually polymers, especially for water treatment, because they are the cheapest. We have the ceramic membranes, quite expensive in comparison. We have also the metal oxides and the others, but they are also expensive as well. With terms of the fabrication, there are different ways, of course, also fabricating and developing membranes from sufficient metallization to phase inversion to packaging and electrophilic. In our lab, we use the phase inversion to make the flat sheet membranes. These can be used for full-time water treatment and desalination. And we also have the electrospinner that we can apply for water treatment. And both of them are quite interesting actually. So with respect to the membranes, it's not really that simple and it's not that basic. This is an hour membrane, and an hour membrane consists of 3 different layers. The very top layer is the active layer, which is made of polyamide. It is active because it is extremely dense. It doesn't has a very low permeability. So water passes through very slowly. However, it's very highly charged, and therefore it doesn't allow any of the salts to pass through. In comparison, these 2 other ones are only there as support. They allow everything to pass. And we need that because we would like to produce as much water as we can with as little salt in it as well. So probably talked about this. This is the flat sheet phase inversion membrane. And because we use nanotechnology, we have different ways of enhancing or functionalizing the membrane. One of them is adding the nanomaterials inside the soil jet, and then we do the casting, producing this very well defined membrane. Another way is we make the membrane first, and then we cast the nanomaterials at the top. Whether we etch it, or we cast it, or we coat it, or we dope it, depending on what kind of work we need to do. Another one is the electrospinner, which is we need a very high voltage, that we make fibers, nanofibers, something like this. And again, in here we also can do different ways of enhancing these membranes using nanomaterials. Whether again we put the nanomaterials into the solid gel and we make the fibers as such, or we can have a cross shell setup where we do the membrane first and then we do another layer of the nanomaterials. Membranes are used all over the world. There is a lot of work done for membranes. Unfortunately, we have a problem with fouling. There is a lot of fouling, and it's very problematic. And this fouling could be because of colloidal or organic matter or inorganic matter as well. And we also have scaling. Scaling is a big problem for brackish water treatment, and sometimes even wastewater. Fouling occurs in different ways, and that's why treating it and removing it is not easy. We could have absorption or blocking or gel-pick formation. And the fouling consequences is very severe. Membranes are usually made to survive for 5 to 7 years. I've seen wastewater treatment plants and desalination plants that have to change their membranes in less than 6 months. It's a huge, huge investment because these membranes are expensive, and imagine changing, instead of changing them every 5 years, you are changing them every 6 months. That's not going to work. And this is why we try to make different fouling prevention. Some of them are using free treatment, and for any kind of wastewater treatment or desalination, we always have free treatment. Unfortunately, it's not enough, and that's why we also do membrane modification. And this is why we do nanomaterial enhancement to modify these membranes. So nanotechnology has a lot of applications in water treatment. We use it for remediation and purification. We can use it also for infection and filtration and desalination. This is one of the using the EU nanoparticles for sensor as a sensing material. We can also use the metal organic frameworks for treatment. And of course, there are a lot of applications as well on that. And this is why the publication rate has increased recently in a big manner. There are many different nanotechnology processes. In our lab, we don't really do all of these kind of desalination. It's not possible. There are a lot of applications, a lot of things that can be done. So what we do is nano disinfection, functional membranes, and a bit of nanosensors and photocatalysis. But there are also nanoabsorbents and filter catalysis that are also a lot of work is going on. Each of them has their own advantages, but unfortunately they also have their disadvantages. And we need nanotechnology because they actually for low or very low secondary resolution. They are also low cost in comparison to how much they are going to produce and compare to conventional treatment. They work very efficiently. And with respect to membrane modifications, there are different kinds of modifications. What we are interested in is the nanomaterials, whether we look for metals, nanomaterials, metals, or carbon material. And this is where we get to the work that we do. Membranes need to have a lot of properties, very important properties. And nanomaterials are used to enhance one or more of these properties, whether we talk about durability, mechanical strength, stability, problem resistance, rejection, and more structural and porosity. And of course, also we have this photocatalysis that is new with the use of membrane technology. And these are some of the things that we have studied in our lab. Using carbon nanotubes, carbon oxide, zinc oxide, and hydrogen oxide, and other nanomaterials. Unfortunately, using any of those, we will enhance some of these properties, make them very highly capable, and unfortunately, they also reduce the use of membrane because they use some of the other aspects of the membrane. And so it's very tricky to work with membrane. This is where we get to the application that we have. This is one of the first applications that we have had, which is a nature system. You know that it is high quality. And what we have done, we give zinc nano zinc oxide, nano particle, and then zinc oxide nano, and we convert it into super high quality. And we use this to in any oil water system, and it cuts the oil, but keep the water in. It's super high quality. It doesn't allow water to pass, only allow the oil to be absorbed. And this we have a patent and they take in incorporated in 2018. Another one is polyethylene with high convenience dioxide. And you can see here this is an anti-fiber and the nanomaterial. And with this, we increase the use of the nanomaterial, especially high convenience dioxide, increase the chemical flux and increase the water flux level and high absorption for productivity. But not only they increase the flux, but also increase the rejection and go more than 98% rejection of oil in water. Another thing that we have for catalysis, photocatalysis is basically using UV light, which is obviously quite expensive, or using solar light. When you use solar light as a source of energy, you get the organic material, and you use the semiconductor light, and you have these holes and gaps, hydrogen groups that are capable of liquidating the organic matter, leaving us as the water. And this is what we've done, and means the work that we have done. This was research that we done in the marina and we had close to 100% this description of my work in the marina and my microbiome and microbiome. Another one is scientific guidelines and actually we have achieved more than 77% of organic and other organic because we use titanium titanium at that point. Another one of those is using the zinc oxide and the great thing about this is even though zinc oxide is only capable of creating organic matter and this is with solar light because it's photoactive. It's not only a biocide, it's not active in itself, it's light as a source of energy. However, when we tested it on our lab, we actually found that even after 48 hours in the dark, it had 100% efficiency. So this was great because with this, we don't need disinfection. We don't need fluoride disinfection or other kind of disinfection. The membrane itself is self-cleaning, it's self-disinfectant. And therefore, we don't expect disinfection by power. And the thing is, in the desalination, 80% of the product in the desalination always comes from the material in the water, even after the disinfection. And this is something that we have done with your zinc oxide and all. And this is what happened. You see, this is the nano zinc oxide nanoparticle of the membrane. This is the zinc oxide nano of the membrane. And you can see that when you look at the fluorescent microscope, you can tell that the bacteria at the surface of the membrane, when there is no nanomaterial, it is clean, and therefore the bacteria is live. It's alive and it's thinking, it's reproducing. While the other side, with the nanomaterial, especially with the nano here, all are dead. And this means that the stay there and doesn't produce. And this is why we call it self-healing and self-disinfecting. This is one of the other ones that we had using carbon nanotube, and as we can see, we had not only higher production rate of water, we also have very high rejection, and we have very high disinfection as well, which is good. You see, but this is the carbon nanotube that are organic, PES is organic, and we have a very big problem making these membranes. And this is why we had to make our own carbon nanotube. We had to provide for our own parents because enough of the commercial ones couldn't be used for this. So where does this leave us in the application of functionalized membrane and the application of nanotechnology in water treatment, wastewater treatment? What is still not there? We always say that future is coming, the future is bright, and we have been researching here for more than 10 years. There are big groups all over the world, bigger than us. Some of them probably are here, some of them are not. Everyone is working, but until now we are still in this PR and 4 process, which is technology validation after technology demonstrated in the development environment, whereas the conventional parts are already applied in real life for almost all of the nano-enhanced processes, whether it is membranes or any kind of nanomaterials. We are still here in the PRL 5 and 6, which is unfortunate, but I'm hoping that we, in the coming few years, hopefully something will be to what we will have this. And the problem of that is because of the cost uncertainty. We don't know what's going to happen next. We don't know how the change of the market is, what will nanomaterials, how will it change. Most of the nanomaterials are actually synthesized in-house. They are not commercially available. None of the commercially available nanomaterials are suitable. The other thing is scalability. When you do any kind of research, the first part is, of course, in universities and research staff. But afterwards, it has to move to the industry, and the industry have to invest big money so that they have a bigger scale of production, which is not something that we have because the industry is happy with the processes that they have most of the time. We need process development and innovation. It's very, very important. We have the competition with conventional technologies, and we also have environmental situation. So consider subscribe, for example, is not only toxicity area. It's good or otherwise. However, if we use it, for example, and use it on the sea, what will happen to the sea life? How will of course, the public perceive it, how will the government perceive it, how will the NGOs also look at it? Because you don't just have anything you want. It has to be studied and has to be reviewed. And this is why one of the problems that we have. From a total of 1,356 photocatalysis and water treatment, only 29 of these, around 1,400, were with a hydrated system, a small water system. Everything else is just in the lab, small research in the lab. And this takes into, this is another thing which we always have a very big ability of everything. We always have a very big hype, say, wow, this is amazing. But the inflation leaks us somewhere, and then we realize that this is not going to work, and everybody starts attacking it. However, there will always be a niche market that can be applied for. And this is where many people are looking at. This is where we are looking at. We are looking at an application of nanomaterials and enhancing membranes. And these are some of the future prospects identified in each market. We need technology integration, large-scale comprehensive analysis and long-term operation. And this is what some part of what we are doing now. We are looking at the combination of this kind of hybrid water treatment and desalination in one system. Using capacity ionization, using membranes, water catalysis, and renewable energy in one system. Trying to make a prototype for this to see how much can we get out of that. And with this, I end my talk. Thank you very much for coming.
One or two questions, please.
We look at many different now. We have carbon nanotubes, graphene oxide, graphene, magnetic, and amperic. Yeah. But unfortunately, with graphene is not, those are graphene membrane, and they are still in the body acceleration phase. Yeah, it's in the body, yes. Yeah, thank you very much. Also, graphene with the membranes, they don't really mix well together. So you will need to reduce the graphene oxide, reduce graphene oxide. Otherwise, it's not going to work with the polymer. Well, it depends. Many people, they will say yes. I'm not in the place to say yes. I am not fond of it. But water desalination, yeah. If you, well, in Oman, more than 96% of the domestic water is from desalination. But seawater desalination or groundwater desalination, not wastewater. We don't do wastewater desalination in Oman. We do tertiary treatment, and then we use it for recreation and so on. Yes. Reject from for wastewater treatment. One part of the reject that we do is we make fertilizers out of them. But now recently there were advocates saying that these fertilizers are not safe anymore, they are not organic and all of that. But usually we use them for fertilizers. We treat them further and then we use them as fertilizers. We don't get rid of them. Yeah, they stay there. For the biofarm, what we have is, it really depends. So what we have then, we use silver, because silver is biocycle, and we work on 99% structure. With silver, nanoparticles in the membrane. We also did titanium and zinc oxide, but with photocatalysis, and also with more than 99% structure. However, with photocatalysis, you work with the light source. So applying this analysis is easy, but moving it into the industry is going to be very challenging. Thank you.
On behalf of organizing the research on both the moderators to give a content to speaker.
And then Dr. Technology is appointed as Assistant Professor in the Department of Chemistry, IIT, 6 September 2021. He graduated with a PhD from the Association for the Generation of Science in 2016, followed by 2 successive postdoctoral lectures when Korea University, NATO, Israel, and the University of Manchester, PSC. His current research interests stretch over supramolecular chemistry and material science, and presently he is actively working on the development of metal oxide related to supramolecular architectures and interlocked molecule scaffolds for energy storage applications. Over the years, Dr. Technology published 25 peer-reviewed research articles, reviews, chapters, and patents in the leading society journals, including Journal of American Chemical Society, Chemical Sciences, and International Medicine, Chemical Communication, Journal of Organic Chemistry, Inorganic Chemistry, etc. He already received the SRM Startup Research Grant 2024 and the IIT Tripoli Grant 2022 and 2025 to start independent research career at IIT. Now I welcome Dr. Sadasivuni.
Thank you for the kind introduction. Today I am going to talk about metal oxides, and I want to show 2 different metal oxides and how drastically their behavior is completely different. So as you can see from the title of my talk, which is so transition metal oxides from self-assembly to surface activation, 2 completely different phenomena, yet it is possible with 2 metal oxides which fall in the same group of the periodic table. So as I did my PhD in supramolecular chemistry, and the thing that I do or I did mostly falls around the supramolecular chemistry, and we know for the last 2 decades is almost metal organic frameworks and organic frameworks, and we were working on many things. But these 2 examples will justify how metal oxides can be functionalized, or how we can control the cell assembly inside of metal oxides. So, what is supramolecular chemistry? It is basically chemistry beyond molecules, where we have development of functional complex molecular architectures to give certain phenomena. So the main objective is to prepare the novel functional systems. And in this regard, we know in 1987 that the first Nobel Prize was awarded to 3 professors, Professor Ronald J. Grant, John Mary Lane, and Charles J. Pedersen, for the development and use of molecules with structure-specific interaction of high selectivity. What they did, they basically developed tryptophan type of molecules or scaffolds, and unfortunately they got a yield of 0.4%, and that 0.4% when they isolated and helped them to get a Nobel Prize. So if you have less than 1% impurity in sample, don't throw it up, you might get a Nobel Prize, right? And one of them got that. So apart from that, there are a lot of discoveries in this field from by Cram, this hemicrystal, and then circular self-assembly by John Mary Lane, then paraxylene and diammonium, which is the tocopherol, then rotoxins, which is like around 20 years back from now, which is actually developed, and then catenin by Stoddard Sauvage, and then Folderman by Newton. These are the pioneers in these fields, which they all started to grow with time. But the question is, still for the last 30 years, we are still focusing on this kind of interactions, 5 basic interactions: hydrogen bonding, halogen bonding, then hydrophobic interactions, dipolar and electrostatic interactions. And you don't believe me, for the last 40 years, this field is only sustainable on these 5 interactions, which are pretty basic, and it's a lot of functionals, and there are a lot of functionality that involves in this, and it actually gives a lot of potential for application also. But what the question arises, it was the first Nobel Prize in 1987. Do we think that it is really died? So that's the question. How does the Nobel Prize go? So, but the answer is it has got more to deliver, and that is why in 2016, again another Nobel Prize in chemistry, this is Professor John Lennon, Professor Rotter, and Professor Ilika. And what it did, the first lot of scientists got the Nobel Prize, they developed the structure-specific models. And these guys actually use those for some applications. So what they did, they mostly developed interlock techniques where a clear mechanical bond movement was possible. And that was the reason why within another 3 years, this particular system got another prize. So this was the worldwide solid where we can see two independent magnetic cathodes actually stitched together through mechanical non-covalent interactions by demetallization state, and this was why the geometry solid. Then this is why Dr. Sadasivuni, where basically again this like an interaction actually allow the on-off or switching of this magnetic characteristic from one compartment to another compartment, and also the detecting of this kind of charge species from around 0.7 nanometer of height just by the electrostatic interaction with other particles. And with that, then Professor Sadasivuni actually developed molecular motors which can revolve around 12 million revolutions per second. It is so fast, and that was they actually developed an artificial nano car with this kind of used as a wheel in those kind of systems. So basically, it gives us an idea from the 1987 to 2017. The field actually developed in such a direction where you need to go for applications, and there are a lot more to deliver. In this introduction, what I want to say, the supramolecular chemistry is nothing but the teamwork. So all the molecules has to work as a team with the other team to give you a proper application or proper feedback that actually can be used for different applications. So when I started my journey, so I was mostly interested in anion recognition. From there, I mostly moved to metal oxides, and I usually work on soluble metal oxides clusters, which are called as polyoxometallics. These are nothing but polyatomic anions with mostly group 6 and group 5. These are all oxides. Today I will talk about molybdenum 132 specifically. And the easy part is that they are highly water soluble, and you can use an NMR as a technique to see what's going on in their chemical environment. In doing so, there are plenty of different cluster structure available, like from liquid structure, which I am specifically interested in, and currently my group is working on this. And apart from that, there are different kegging-based anions, kegging-based metal oxide clusters, and as well as Dawson metal oxide clusters, where you have some doping element, heteroatoms like phosphorus, silicon, aluminum, arsenic, and antimony. Those are doped, and their chemical properties actually changed with these doping kinds of things also. And this whole building block is how these structures are actually, or how these metal oxide complexes are actually made. That's a big black box question, because what's going on in the solution state at a low pH or high number temperature is really hard to fathom or to find out, and that was really a challenge. But what we know, that every MO4 unit, metal oxide unit, or a tetrahedron comes closer together and stitched up, and usually brings these robust structures, and these are very specific and sensitive to particular temperature or pH of the solution. And you can also have this bottom-up approach to delete this metal oxide fragments from your cluster to create a vacancy where you can do catalysis or any kind of anchoring activity. In doing so, today I am only going to talk about this beautiful football-like structure, which is known as molybdenum 132. It has 132 molybdenum centers, all bound by an oxygen or oxides, and where you can see you have basically 72 molybdenum 6 pentagons like this, where you have 72 molybdenum 6 centers, and you have linkers like this, where you have 60 molybdenum 5 centers. And these molybdenum 5 centers are actually bound by this kind of acetate kind of molecule, where carboxylic acid. And this is actually an interconnection from both oxygen centers donated from acidity to both the molybdenum 5 centers. And in the whole structure, the size is somewhere around 2.9 nanometers, close to nanometers, and you have these spokes which actually allows your gas to go in and bind the molybdenum center. And Professor Ashok Kumar, Germany, actually started working with this now. Professor all of them are working vigorously on different higher molecular structures of this from 132 to 368, 350, different classes they work on. But what I was interested in to see how cell assembly inside this can be monitored and by a very simple observation. So for that, what I want to say that suppose when we dissolve alcohol in water, so there is a hydrogen interaction that is going to be promoted, right? So usually what we see when you dissolve alcohol in water and in presence of an acid, usually this phenomena is inhalable. And you can see the interaction alcohol is minus 20 kilocalorie. That means when you dissolve HCl ethanol, then what you get is the H plus, that is the drives the thermodynamics and it becomes an inhalable phenomenon. So what happens if you use the similar way, but instead of the bulk environment, if we do this inside the confined environment of that molybdenum therapeutic acid, what it does. So basically what I want to do is I want to displace the additives which are bound inside in this molybdenum 5 centers, 60 such kind. And as I said, there are 30 acetate or RCO minus liquors. I just want to replace them with an acid which contains an alcohol group. And in doing so, instead of acetate, I chose formate because formate and glycerate has a very similar pKa value. So there should not be any pH driven favor towards any of the host, any of the exchanging gates. So that's why acid formate and glycerate pair was chosen. And from NMR, you can see the different ranges where your glycerate is inside or outside. So when it is outside, it's more downfield shifted. From the same scenario is for your formate also. And a typical situation where the molybdenum alternative persists or stays somewhere around from a pH of 6 to that of pH of 2. So what we did, all the studies were done in diluted water, this D2O. And of course, you cannot use the pH in that scale. You have to use the PD. So the diluted condition of that. So if we start with a high pH of let's say 5.8 in this scale, and we see that almost 19 formates are sitting inside, along with 9 of the glycerides. So out of 28 ligands, mostly are the formats which are inside at a PD of 5.8. And we are going to use a simple thermodynamic relations, that is, if the glyceride has to go in, it has to bind to the molybdenum center. And if it binds to the molybdenum center, the acid format has to come out. And once it comes out, you will get the idea from the MR. And obviously, you can get the idea about this pH change from your pH meter, laboratory pH meter, because it will have a bulk pH change as well. But we will be using buffers to maintain the pH completely stable. So in doing so, what we first take is the Bancroft plot to see what happens to the temperature. We go start this same thing at a same exchange phenomena at a pH of PD of 5.8 at a low temperature, let's say at 10 degrees, and we increase it to 50 degrees centigrade. And you can see the equivalent of formate at 10 degrees is way too high. It's somewhere around 25 and only 3 glycerides are allowed. The moment you start rising the temperature from 10 degrees to 50 degrees, you can see the number of glycerate going inside increases abruptly around 27 and 28, and almost close to 1 or 2 equivalent of formate is going in. This gave us the first idea that this exchange phenomena is thoroughly driven by temperature, which is a part in when we talk about thermodynamics delta G P energy relation, is a part of the entropy, not that of the enthalpy. So from there we got the first view that there could be an entropy factor that's actually playing here, and we also did the Bancroft plot where we got a straight line, and from there we calculated, as I have shown you, exchange equilibrium equation. From there the delta H and P delta S values were calculated, and what we found is that the delta H is just a little bit excess to that of the minus P delta S. That means the delta G is very close to that of 0, plus 0.7 kcal per mole, right? So from there when we start, then we want to see that is it the alcohol groups that actually plays the role, or there is something else. In doing so, we screened 3 different kind of gases, starting from glycolate to lactate and glycerate. And what we saw, if you maintain the same pH, and if you change the gas from CH2 to CH3 to CH2OH, you see there is a drastic change in the uptake capacity. The moment you increase the number of OH groups, you will see the which the guests are welcome more inside the cluster compared to the guests which have less amount of OH loads. And this whole phenomenon is completely reversible. We can start from a pH value, PD value of 5.8, slowly increase the pH by a controlled addition or the concentration of HCl, and go from 5.8 to 5.4 to let's say 5, all up to 3. You can see the number of glycerate going inside will increase to 24 and 25. The same you do the reverse thing. You start from pH PD3 and start on adding like known amount of NaOH, and you reach the same page, you will see the glycerides will start coming out, and that was completely observed in AMR. So this whole system is completely in a beautifully equilibrium situation, and that is only controlled by the pH, or that is the H plus of the system. And we also calculated the zeta potential on the surface. At the PD of around 5.8, you can see there is almost 13 glycerate to 15 formate inside at PD 5.4, and the zeta potential value is minus 31. The moment you decrease the PD of the solution to that of close to that of 3.3, you see the zeta potential is minus 10, and the glycerate inside is 24. Almost doubled compared to what we saw at PD 5.4. That gives us an idea. The zeta potential is the surface charge, right? Signature of the surface charge. That gives us an idea that there is some cation that is actually assisting this zeta potential reduction, and that was activity of the glucose that I will show. So we did a lot of literature studies to us, like me and my team needs almost like 6 to 8 months of thorough literature study to find out the proper equation to this kind of thing. And we came up with this simple formula which we studied in bachelor's degree, that the PD calculations has to be derived because of the hydrogen oxide, and obviously the same pKa has to be also selected because of the pKa. Along with that, your pH relation has to be modified because of using PD instead of pH. Based on that, what I want to see is I want to replace the formats with data of glycerate in presence of protons. And I am using a very basic and simple infrastructure, just a pH meter to see what the pH going on, and an NMR tool. That's it, nothing else. With this, and I know how much concentration of the radiant that I am adding to, and when you know the pH and when you know the amount of proton or acid added to the system, so the pH is the bulk environment pH, you know how much proton is added, just simply deduct it. You will get how much proton is actually going inside of the capsule to acid this and with doing so, what we saw, there was a change, and this is the amount of acid added to the system, and it was minutely, because all of these reactions were done in MR tube and proper precautions and proper calculations. So we increased the proton concentration from 25 millimoles to 200, and those proton added were distributed within the capsule and outside of the capsule. So from outside the capsule, the pH will be the stream, how much of the protons are there. And if we plot that what is the ratio between the concentration of proton by the concentration of glycerate inside with the pH or PD, you will see you will attain almost a plateau around 3 or 3.5 PD value, which is the close to the pKa value of your gas, and that gives you 1 proton called glycerate that is being assisted inside the cell assembly of this whole system. And we got the crystal structure of this also, where you can see the water molecules are in those hydrogen interactions with the OH groups as well. And then we extended Vector analysis on all the PD values, and what we saw that the delta H, you can see it is decreasing, right? And the more we decrease the PD value, the delta H is decreasing, and T delta is, of course, it has to be decreased because your gases are going inside hydrogen interaction, their motion is restricted, the entropy has to decrease, that's what decreasing, but the magnitude of PD delta is much higher compared to that of delta H. So that was the delta G becomes much more negative. So starting from 0.7 kcal, it goes up to that of minus 3 kilocalories per mole. And the surprising fact is that when we do cell assembly of micelles or anything that hydrophobic things, in water we get the cell assembly is usually entropically different. But this is a case where a highly hydrophobic molecule doing a proton accessory cell assembly inside a molybdenum capsule actually giving you a subatomic signature of a hydrophobic cell assembly. And it was remarkable and never been observed in the research that it was published in JACS in 2019. So this was the work with molybdenum-132. Then this was the same assembly inside a molybdenum-132. Then I was interested to go to 3D transition and see whether I can activate vanadium oxide bonds or metal oxide bonds, because molybdenum oxide or calcium oxide bond activation is really tough. These are very strong bonds. So what we want to do is to model the surface of vanadium oxide material which are used in glass industries and heterogeneous catalysis industries, meaning heavy industries also. Vanadium oxide materials are extensively used. So I wanted to see what's going on the surface of the vanadium oxide cluster. And in doing so, I started with this kind of cluster, which is called liquid vanadium cluster, vanadium oxide cluster, which is B6O7O-methoxy12. And these are the molybdenum cluster. The beauty of this cluster is it can go for a 4-electron redox process, which is absent in molybdenum cluster cluster. You can see this is a vanadium process, and it can start from -2, where all of the vanadium centers are reduced to class 4 oxidation state, and state can come to 5 vanadium, 4 vanadium, 5 and 2 vanadium 4 centers. So that was the main reason why I chose this polymer vanadium kind of thing. And in literature, there was known that proton-assisted proton-coupled electron transfer from like 2000, late 1980s or 1990s. But nobody showed what's the pathway of doing a proton-coupled electron transfer. And there was, this is 1954, what they said is that if you have a vanadium oxide or any metal oxide material, you cut out one of the oxygen and you add a carbon dioxide. This was mechanistically done. No theory on the experiment. And then carbon dioxide is absorbed, followed by the presence of a proton. And that actually gives you a value-added product. This was the theoretical prediction almost like 70 years ago. And since 1987, people are doing these proton-coupled electron transfer things very difficult to understand what's going on and how mechanistically this is going on. This is very important. And so what I want to do is to cut down this vanadium oxygen bond and see whether I can mechanistically study this field. So in doing so, what I did is I started with the vanadium cluster where you have only one vanadium 5 center and 5 vanadium 4 centers, where you treat it with V-methyl-3 and you get a vacancy. This is highly reactive, and this is quite easily you can see from NMR where you have the peak, because it's an octahedral complex, the peak is at 23.2.
2 minutes.
And it peaks around 3 peaks. So you can generate this kind of vacancy pretty easily. And there are certain examples that proton-assisted or chemical-assisted, radical-assisted reductions of these clusters are possible, but the pathways were never been told. So this is what people was expecting, that if it goes to the reduction from here to here, then it has to go through a hydroxide pathway. But it was this hydroxide VOH. Hydroxide was never been isolated. So what I did is that instead of OH, I want to substitute with OSiN3, because SiN3 is considered as a sulfate of proton. Right? So the behavior will be the same. And in doing so, what I did, I used TMS to OTF, which is instead of H class, we are using TMS class. And you can see it's in frozen condition, minus 95 degrees centigrade. And you will get this. And from NMR also, you can see it's beautifully splitting. 36 protons are there. All of them are equally splitting 12, 12, 12. And that gives us an idea that we have, say, synthesized something like OSI, which is like protected, and we got the crystal structure of that also. And that also matches the XPA study, where you can see all the vanadium centers are actually in that class 4 oxidation state. But in case of V-chemistry, it was not possible because we are going to class 3 and mixture of class 4. But here with civilization, we got all of them in class 4, and this is highly unstable. Within 6 hours in room temperature, DCM solvent, it breaks up and creates your parent cluster. So 2 SiN3 cluster come close together. One goes back to B-double-bond-O, the parent cluster. Another forms your trimethyl ether, TMS2 and with the CV signature, where you can see the reduction of these centers were possible at minus 1.08 to completely go to all 36 centers which was never before. So this was also, we can reduce it further to generate 2 minus clusters also, and that was also isolated, so you can reduce it, the 1 minus cluster to 2 minus cluster, and also you can oxidate. So this gives us a question on the previous mechanism, or in case of material science where people say proton injection only comes after electron injection. So you have to load the electron first, followed by the proton, then only you get the PCT. But what we did here systematically from 2 minus to 1 minus to 2 minus. So instead of going step by step, what we mechanistically do, this is not a proton couple, this is not a electron transfer followed by electron transfer, but this is actually a proton couple to electron transfer, mechanical couple electron transfer process, and this was a publication chemical science. And that's it. Thank you. And I want to acknowledge all my agencies, and I want to questions.
One or two questions, please.
Halogen bond is between, suppose you have a limiter zone and you activate that carbon between the nitrogens with the CH, where X is an halide. Let's say CI or C here, and then you add a tetraethyl ammonium chloride or tetraethyl ammonium halide, that will bond with that bromide or iodide which you have functionalized, because the limiter is here, that that's the electron density from your bound carbon iodide bond, and I is that carbon iodide bond that will take a cluster. That's why when I minus comes, it belongs to that. Professor Quality here in Oxford is extensively working on that, and I also published papers on that, but he usually uses that for mechanically the molecule synthesis of chemical. But this is Professor Dr.Sadasivuni in IISc initiative with Professor mechanism as well.
On behalf of our organizing committee, I request once again both the moderators, please hand out the token of our affection in the form of momentum to the speaker. Thank you. I request us to invite the next speaker.
And then since December 2022, we have been working there. Before joining, we worked in the Department of Chemistry in different capacities, what I mentioned, 31 years. And then he served as principal, and he has gone as a principal cadre to other places. And we have some. So you will have to say. And then he has received his master's degree in 1988 and PhD in 1992 from Andhra University, and he has been a distinct scientist at the University of Dhaka. And then South Africa, and afterwards he had postdoc research at the Institute of Inorganic Chemistry, University of Leipzig, Germany. And after that, he has postdoc research in Taiwan also. And after achievement, he visited several universities in USA, Canada, Japan, Australia, and Singapore. He received the researcher award twice from University in 2010 and he published about 70 research articles in national journals. 9 students have received PhD degree under his able guidance. He received research grant for 8 research projects from DSP, CSIR, Ministry of Petroleum and Natural Gas, UGC and UGCDA. Thank you very much.
Session chairman and conference chairs, Kishore Kumar and Professor Anima, and my students are very good afternoon to all of you. So this is a very crispy presentation. So basically, recently I have moved to this university, Central Tribal University. I think Ariharna already mentioned for the last 31 years I worked here. What are the going to present this work is from here, this university. So I wish to say some research findings here. Hydrogen storage in solid adsorbents. We have synthesized some solid materials, adsorbents, either MYF materials or the carbon material, and we examined the storage capacity. Why the hydrogen is a feature of the fuel? So you know the present scenario, the hydrogen is an energy carrier that can transform our fossil fuel dependent economy to the hydrogen economy. So we can provide the emission-free transportation. So you know the importance of the hydrogen and moving to the fossil fuel, the economy to the hydrogen economy. The hydrogen, after burning, the hydrogen gives only moisture to the water, so without carbon dioxide. So when you see the present scenario of the carbon dioxide in the environment, so this is the recent data, July 4th, there is a 422 ppm, the global carbon dioxide level is 400, more than 400 ppm. It's a very, very high alarming level. So that leads to so many environmental problems. So how to control this carbon dioxide? So one of the route is to apply the hydrogen. And you see the history of going to the net zero. So when here there is in 2015 the agreement, the meeting conducted in Paris. So then there is to reduce the carbon dioxide levels in the environment. So towards the road towards the net zero, the given path how to reduce the carbon dioxide levels and to protect our globe. So in this case, these are the various routes suggested, and ultimately this is the target for 2050. So we have to use only transmission to the net zero emission must be fully. So we have to doesn't produce any carbon dioxide, either transportation or the industry, any reactions. So that's why this is the roadmap. For that, what we have to do? So we have to find alternative fuels to reduce the carbon dioxide levels. So when the hydrogen, why you have choose hydrogen? So when you look into the hydrogen is an energy carrier. So it can be a major fuel for both mobile and stationary power, either used for industry purposes or for the transportation. This is one of the best fuel, the eco-friendly fuel. And when compared with the gasoline or the petroleum fuel, is the highest energy carrier. So 143 joules per kg is compared to the gasoline. So one of the major fuels we can consider. The one major hurdle for using this hydrogen is basically storage. How to store this hydrogen is one of the hurdle, and the thing is minimum 300-mile range is required for the transport. So what are the different kinds of hydrogen when you produce it? Now we are recently focusing on the production of hydrogen. So these are the various types of hydrogen producing different hydrogens in the different colors. So these are the major three routes. One is the grey hydrogen, blue hydrogen, and green hydrogen. So using the natural gas and produce hydrogen, leaving the carbon dioxide in the environment, but it's not good. And the other route is using natural gas and then producing hydrogen and stored in the CO2 mitigation. Through the mitigation process, you can store carbon dioxide in underground. This is somewhat better, but this is the best way. Without using natural gas, by just water splitting, you can convert the hydrogen. Simply, you doesn't produce any carbon dioxide from this. So, green hydrogen is one of the best pathway to produce the hydrogen and use for this route. So, this is the green hydrogen. Suppose when you produce it and transport, and you can apply in a different applications. The end use is industry, you can use transportation purpose, heating, and power generation. So for all these purposes, you can use it. So this is one of the best way to use the green hydrogen to reach the. It's one of the best way to reach the net zero by 2050. Then use green hydrogen. So then recently in India, Modi, our Honorable Prime Minister Modi is also taking initiation. The January 2023, they released about 19,744 crores released to the hydrogen mission, the National Green Hydrogen Mission. So you can use the green hydrogen. Recently in the USA also he mentioned this green group. India is also following the same procedure, producing the green hydrogen. So released this through the National Green Hydrogen Mission. So the aim is 1 lakh crore cumulative reduction in fossil fuels. You can reduce the fossil fuels when you use the hydrogen, and then you can reduce the greenhouse gases. So this is one of the ultimate goal of India to use the green hydrogen. These are the various routes. I am not going to focus on this. This is the different types of routes I have already mentioned, and this is the green route, green hydrogen route to synthesize. So we will focus on the storage behavior of this. So our main research activities are that. So the storage properties of storage materials we have to suppose for the transport purposes. The US Department, DOE is given some certain targets. So the storage material, suppose any solid storage material can store about 5.58%. This is the goal for 2025. Ultimate 6.58%. Suppose when a material store about 6.58%, then this is capable to use this material to run in the transportation purposes for about 300 miles range. So this is one of the good application, but the only thing is we have many challenges to reach this. So these are, maybe you know already in the internet also you will get this information. So these are the various types of materials, the hydrogen storage materials, physically you can store it or the material basic. Physically, where all these kinds of materials, either physical storage materials or the solid materials have a drawbacks and advantages and disadvantages. So when you see this one, recently some of the transport vehicles, either car or some other vehicles, heavy vehicles also, they are trying using this physical storage materials by using a cylinder. But the disadvantage is you have to keep this gas at about 300 to 700 bar pressure. It's a very high pressure, maybe like a bomb when using in the car. So this is the disadvantage, but very good application. The another one is storage in a liquid form, but this is also not viable because this material you have to keep this liquid at very low temperatures. So you see minus 252 degrees or minus 177 degrees. So it is very difficult and not viable to use these temperatures. So other side is we have to develop. Suppose when this kind of material, physical storage materials we can try for the storage applications, the other side storage in surface of the solid, physical storage materials. Basically, my work is in this direction. So we have before that the chemical storage at the bed and the physical storage at the bed. Basically, I think you know it, the pros and cons and the advantages and disadvantages. The chemical storage materials like the hydrides or some other nitrides or colloids and nanoparticles, they can store more hydrogen, maybe 6.5 is sufficient, but it can store 9%. But even though the problem is you have to use high temperatures, 200, 300 degrees temperatures, you have to apply to release the gas, to release the hydrogen from the material. So this is also, maybe you have to work it, some of the scientists are also working on that to reduce the temperatures and to store more hydrogen. And the other area is the physical storage material. So this is we are focusing on it. This also, but this stores very low temperatures. Either MOF materials, some are not that much stable. But hydroscopic, many of the MOF materials are hydroscopic. But this MOF materials, metal and flavors, can store 7.5 or more. But the problem is these materials can store works at 196 degrees centigrade. When you come to room temperature or low temperature, at least even minus 20 degrees is also good for usage at transport of a bus. But the storage capacity is about 1 or 2 buses. That we have to work it out to improve the storage capacity of this material. So we are focusing on these 2 areas. One is developing MOF materials and carbon nanomaterials. So this, I think this is also a common information. The MOF materials, the area they worked in this one, MOF 177 is one of the starting with the best material developed by Omar group that developed this best MOF material. Can store about 7.5 weight percentage at 7.5K. But the room temperature is about only 2 or less than 2. So this is the procedure. I think this is the common procedure. Everybody knows how to synthesize an metal and prepare the material. So through the hydrogen techniques, you can use the autoclave and then take the metal precursors and then ligand, then heat it to 180 degrees centigrade for 2 days and finally pressure. So through the simulation analysis, you can find the structure of the material. So this is one of the techniques to synthesize the MOF material. So in this direction, I have received some grants from the Ministry of Petroleum and Natural Gas in collaboration with the HPCL. And I worked on it. So some of the MOF materials I have developed in my lab. So we almost not a good materials, maybe we issue 3 to 4% at 7K and maybe very less around 1% at low temperatures. We have developed some MOF materials in my lab. Some of these materials, maybe not going to too much information, maybe. So we patented these materials and we received 2 patents from Gary. And the other area we focus is carbon-based solvents for hydrogen storage. You know these are various materials, but I have focused on CADs. The CADs, what we did here, we have taken the bare multi-colored CADs multi-word CLTs. So we have functionalized here acid functionalized, make it acid functionalized, then dope the metal on the surface of the carbon nanotubes. This is the basic work. Then later we have examined the surface properties as well as the hydrogen storage capacity, particularly what we have to focus on this materials generally stores more hydrogen at lower temperatures. That is our aim. So these are the SEM, EM images of the carbon nanotube. After functionalization, you can see the spectrum of the CLTs. Then after you can dope the metal nanoparticles on the surface of the carbon nanotube. So these are like this. We exercise many using different kinds of metal. So this one I think I use the iron oxide nanoparticles. We have doped the iron oxide nanoparticles on the surface. The procedure is same, functionalize, and then the metal dope on the surface of the material. The procedure for all the materials we have uses the same procedure. And only the case how to improve the metal doping on the surface. So we have used different kinds of solvents, particularly amine and water and DMF, different organic solvents and different amines and different presence of aqueous medium. And we have tried different solvent conditions to dope more of metal oxides on the surface of the carbon nanotubes, because when you improve the more and more metal oxides on the surface, you can be able to store more hydrogen, absorb more hydrogen on the surface. So this is our aim, and initially we used the, I think you see this, the water molecule for aqueous condition, amine condition, and DMF condition. Particularly in DMF and the amine, we got higher absorption capacity, particularly 0.2, 0.3, 0.4, not more than 1, maybe. So we have did some other. This is also another work is published in the Sustainable Development Journal. So we doped the zinc oxide nanoparticles on the surface of carbon nanotubes. Same procedure will follow. Same solvent conditions, different solvent conditions we follow. And here also we got about 1%, 1.2% and this. So another idea we have, why don't you make a composite materials like MOF and then metal dope carbon nanotubes. So in that direction we have mixed two types of materials and make a hybrids. So when you take we have taken the COBDC, this is the MOF material, and then nickel dope, this procedure is same what I have explained, and then nickel palladium dope and nickel dope mixed with this, then we got this zone, this is the same image, and when we mixed the MOF with the palladium functional nanotube, then we got this material. So after getting the compounds, then we examine the hydrogen storage capacity of this material. So here, simply at 77 K, so what actually the MOF materials store more hydrogen. So that's why at the low temperatures, then we are interested to check the this material at 77 K, then reach about 5.56%, almost 5.5%. This material that's a very good shows a very good capacity. And similarly, we have examined at room temperature 298, the room temperature. Even at room temperature also, we received around 1.5 or 1.6%. It's a good sign, and we have to work it up again. When you reach about 4, 5, 6%, definitely is a good material we can use in future transport applications. So this is the mechanism we have examined the same material. This is a different adsorption, desorption. So we have to check the cyclic performance, because if you want to use any material in the car or any vehicle, so you have to Suppose if you buy the material for 2,000 or 3,000, if you work it out only one time, two times, very costly. So we have to use the same material for a few months or at least 1 year or 2 years. So cyclic performance is also very, very important. So we cannot run more, but in our lab we have examined, but our materials are very good. So sometimes, 10 times we work out. It shows the same absorption performance. I think maybe I am suggesting the young guys, you also work it out because this is one of the good area of research because we have to protect our environment. So we have to go for a hydrogen definitely. So these are, I am thankful to the this UGC and the Center for High Technology, the Ministry of Petroleum and Natural Gas, with the support of HBCL for giving grants for my research. Thank you, Madam.
Another question from the class.
No questions? You may understand better or maybe.
Yeah, I request once again the moderators to give a minute to the speaker. Now I request Dr. to invite the next speaker.
Joined in 2010 after completing master degree in mechanical engineering at the University of Technology, Malaysia, and first class honor degree in material technology in 2008. In 2013, Dr. Sadasivuni was awarded a prestigious scholarship from the government of Malaysia as VRC for young among the top 6 people in Malaysia. He joined the Stevens Group under the supervision of Professor Molly Stevens and Professor David Perry. His project focuses on successful activation of biomaterials using X-ray electron spectroscopy. Dr. Mujahid completed his PhD in 2016 and started to form his research group and addressing challenges of bioelectronic materials, biomaterials, improvement, flexibility, conductivity, and other main functionalities. And he has won several innovative awards, international and national levels, such as MBE and IADX, showing his research excellence for direct applications in the real environment. And his research work was received funding from various sources, including the Ministry of Higher Education, Malaysia, and private funders also. These grants have enabled him and the research group to conduct cutting-edge research, advanced materials, bioelectronics, and energy. The outcomes of his research have potential impact society in significant ways, from improving the performance of lithium-ion research technology devices to developing novel materials for medical applications. I request Dr. Muhammad to give his talk.
So I'll be speaking today on the beauty of conductive polymers that we have explored for the application in bioelectronics and biomaterials. So before that, I would like to take this opportunity to introduce my country. This is some of you might not be that familiar with our country. So we are actually part of the Southeast Asian countries, and we are in between Singapore and Thailand. So therefore, you can see that we are here. So this is Singapore and this is Thailand. So in Malaysia, we have quite a number of public universities, and my university is University Technology Mara, and it is the largest university in Malaysia. It has, so we have one main campus, which my research is based, which is the main campus in Shah Alam, India. So interestingly, we have 12 prime campuses and 21 satellite campuses. So this is how we are at the moment. So my presentation today is on the some kind of you can say that it is an advanced materials which we call it conductive polymer. I think this is new for some of us, but conductive polymer. Right. So in conductive polymer, what we are doing is that the first part is how we navigate the idea of using conductive polymer to be used as a wearable electronic devices. And later I'll also touch on the utilization of another types of conductive polymer, which is PWPSS, for generate future potential in biomedical application. And the last part will be on how we recently, about 6 months ago, about 8 months ago, we explored on having polypyrrole, which is a type of conductive polymer we use to repair. So this idea is now evolving to repair the spinal cord injury of the tissue. So, and I will end up with some remarks. So, distinguished guests, ladies and gentlemen, when we talk about conductive polymer, what are actually the drive for us to explore more and more about this type of material? So the demand of this polymer, which can be used in various stuff, and one spectrum of application includes demand of, we know that the market value is about 3.8 billion last year. So it is expected to have and projected more than 8 billion by this year. So, and this conductive polymer has widely been used in a real application. It has been used in solar and some wearable electronics without we know about it. So, and so we see this is a potential of having some sort of exploration that eventually I'm very sure that everyone and each of us today are doing research for the benefit of humankind. So eventually we want to see that the outcomes of the research can be used and utilized by society. Else we are not doing anything for the planet. So I think we are sharing the same values and principles to make a better world in the future. So, conductive polymers are used in wearable and bioelectronics. So some exploration. After I completed my PhD back in 2016, I started my research group. So in the past, what we do was under Stephen's group at Imperial College London. So what we do, we develop a patch to reconstruct the broken heart tissue. So we use chitosan and we grow the conductive polymer on top of it, and we make a patch. So from this patch, we found that the signal of the cell showing some recovery, and that was a promising observation that we had so far. So when I started my research group, I have actually thinking what is the easiest way to start with. So Dr. Faiz, who recently graduated with PhD, explores the utilization of polyester fabrics, in which we incorporate the conductive polymer, polyaniline, to work as a coating on top of this this fabric. So if you see, this is the fabric, and once we have polyethylene emery base, which is the undoped state of conducting polymer in the blue color. And once you are introducing some sort of dopant on it, you will see some changes of the color. So this is some sort of potential transmission of the color and some functionality in which the conductivity of this material is slightly different. So we have optimized the conductivity for this kind of fabric, particularly the ester, and we found that the value of the conductivity falls within the range of standard conductors. So we are we will kind of theory and further investigation when we are thinking of using the flexible and variable electronic, we should think about how does this fabric actually has the energy properties. So we investigated that how does this fabric work, and when exposed to certain type of bacteria. So these are the investigations that we have conducted in the past, and it shows some positive responses, as in that we saw some and observe the inhibition zone of the different types of the bacteria. Interestingly, how does the bacteria actually kills can kill, or actually the materials that we have formulated in the lab is having some sort of inhibitor. Because in the production polymer that we develop for a typical constructive polymer, it has some certain concentration. So this is dopant are only an acid dopant. So in here, the positively charged of the dopant within the conductive fabric has been killed the bacteria through the light interaction in which positive and negative charge, and it produces some sort of inhibitor properties. So this is an SEM images of the oils, the bacteria, and some rupture has been observed when exposed to our fabrics. When we talk about having more and more extended the functionality of the fabric, which is aimed to be used as wearable devices or wearable electronics, we should think of how it can sustain its functionality. So normally, the conducting polymer that we have can potentially be having or losing some functionality due to the leakage of the dopant within the liquid, especially when exposed to phosphate peroxide, which is the physiological condition, or upon washing of the fabrics. Okay. So what we have observed actually in the past, we have explored the potential of having more cross-link between the fabrics and the polymer. So what we do is that we introduce more chemical treatments to ensure that the fabrics and the conducting polymer remain functional and conductive after several exposure. So particularly in here, after more than 10 washing, we found that the treated fabrics, which is the hydrolyzed fabrics, managed to maintain its conductivity after the next cycle of washing. So this is kind of promising result that we have seen so far. So for the explanation, I invite everyone to come to the device talk tomorrow. So tomorrow at 11 a.m. So he will be sharing some interesting and finding of this system. So stay tuned and look forward to receive your document over the site. So another page student who has been working so hard on having some sort of strength. So this one is collaboration with the technical from University. So Dani has actually had some 200 attachment in universities to explore some sort of the potential of having different conductive systems. So what we explore is that we develop towards strength. So this team is composed of PDE and TDSS. So this is not a new technical combination, but what we managed to find is that we explore the
have the secondary document, meaning that in any conduct document you should have the primary document, which is to use the document to make it more immediate conductive. So when we have the secondary document, we expect that in this case we have the secondary document. So the document is actually works to improve some personality in which that at the end of the day when we make it conductive and variable and also flexible. So we observe some improvement on the interval between the tripod and the PPSS and PVE. So the mechanism here proposed that and improve bonding is actually observed. So I'm sure that when we do some research, we have never always get the best result that we want. So this is the best of our observation within the very time. So we see that some sort of compartment of cognitive glycol when you introduce as a secondary document in PDSS that has the PDE as leading the initial some positive response as it shows more than what was published. So some centering on the screen, which is we need to pull the thinking of them so we can see how much is in here. Moving forward, more from that we explore on how we can use the product point as hydrogen. So in biofuels, we use as drug delivery and more. And more importantly is that it has to be has certain properties including the porosity. So one we are aiming for having more transparent properties in which that the drug flow to deliver to the same part of the issue. We have included the transparency. Some issues in this review is that how does when it is graded over time and how does this actually can work good biocompatible media. So those are the reviews that we have in this review and from that particular drive we have explored of using the So we found that some processes, some of it is an early observation, and because this is just like 1 year and a half. So what we see that there's some processes on the swelling behavior of the hydrogel, and this is after we expose to the EPS, we see some responses in terms of swelling. And as the paper shows that some improvement of the personality, although we know that always or any component should have like a more close fitting, but it shows and some properties on the personality is that more productivity is actually embedded within the system. So we explore how the hydrogen will on the cell, and so from the early observation, I would say more than 80% cells are still alive. This is actually challenging, especially to ensure that the organisms can be like tissue. So we are working hard to ensure and tuning some sort of functionality within the network so that they can extend the sustained period of time. And the work that we have recently published by Hidayah. So what we explore is that how we can the ability of producing the hydrogel incorporating product component. To work as the high quality repair system. you see that this is the spike quadrilateral that is injured. Sorry, but injured by So what we are seeing now, we are expecting to. This is like sounds very niche, but this is what we start. So we want to introduce the hydrogel to review the external, the extent of the alignment between the system, the spinal quadrilateral system. So I'll show you. In this review, we highlighted some sort of the main changes in this is that the case repeating by instance is 5.5 to 105.4 systems. So this is quite alarming, as I mean that it could happen to any of us. And a typical process of recovery is kind of alarming injuries that it is by a total treatment and rehabilitation. There is no specific rehabilitation. So we really send some review, see how this position can be sustained and how this was sustained. And these are the effect of having digital system in the So the current indicator for a spinal cord injury is that. So normally we'll go for physical, occupational, and respiratory, and these are the types of the normal rehabilitation for this kind of case. So, and we think that we should go something that is promising for the future, which we don't know how it's going to work quickly or not, but some sort of effort should be started now. So, and in this review, we mentioned on how we can predicate the hydrogel, especially to ensure that the conductive polymer can be cross-linked with the system of the hydrogel. So this is kind of challenging, and on the physical aspect, these are the most important part, which we have to ensure that how much the hydrogel works to have a stiffness and porosity properties. And in terms of chemical, how the materials is actually stable and pH sensitive and temperature sensitive. So any type of polymer, when we are dealing with human, it is very challenging, as in we really can't control the situation. And some functionality can be embedded into the hydrogel so that we can see how the cell responsive to one particular condition. So we can move one point to another so that any kind of functionality can be correct. So some sort of previous hydrogel has been conducted by scientists, especially on the cytotoxic effect on the hydrogel. And with that, what Hidayah has actually proposed to explore is that we want to create the conductive hydrogel system through a harmonious integration of natural synthetic-based and conductive materials. And this is actually back to the things that I said just now. We want to facilitate the axonal growth with intrinsic directional guidance through magnetically induced orientation without intricate physical structure. So those are the things that we are doing in the lab. And so what we do is we try on having polymer, which is the most recent type of conductive polymer that we are exploring in the lab. And Hidayah turns out to be the first person to explore in our lab. So we have never done this before,
and hopefully we can see some promising results in the future. So we also are thinking that to ensure that the axonal growth can be retuned or can be aligned accordingly when we put the hydrogel in the system, is that we are thinking of including the magnetic materials within the hydrogel. So the reason of having it pretty much clear. We eventually can retune it when we have a magnetic interaction between the hydrogel and the membrane. So those are the ideas. And in the bigger picture, this is what we want to explore more and more. And this is a polypyrrole communicated PEG solution conductive hydrogel. And recently got quite promising structure because it's really take time to get the right formulation. It's not an overnight work, and eventually this is the thing that we want to do. So this is the main purpose of IM and PPY to form unidirectional guidance for the neural regenerative and inhibit random direction for axonal growth. Okay. So Hidayah was so excited because she is the first one to visit the lab, and she sent me this video and compiled it together and how we do the hybridization collagen type, which is non-toxic processing. And we are now finally getting the polypyrrole in here through in-situ polymerization. So how do we mix this component? We do the polymerization right away together in all systems. We don't do like one by one. Alright? So some preliminary data confirm that of the things that we want to have within the big book of the hydrogel is that we use the proximity in which the two components is actually now bind together to form a stable hydrogel. So in here, since we use collagen, and collagen is really expensive to us, and we glad that we managed to identify it, and we managed to get the well-integrated collagen with the functionalities of EPY within the system. So we found that it is conductive as well, and some preliminary is decision in the system. So as for remarks for this particular section is that conductive hydrogel is I said really show some promising for spike injury effect, and a lot of work to do in the future. And if you can see any interesting ideas, just come forward and we can discuss this after. And this is to make sure that the idea can be materialized to a certain extent, and eventually we can hit more impactful discovery eventually can benefit the community. And as a conclusion for my talk today, since I've been doing this since 2013 since my PhD on radioactive polymer, so I see that this radioactive polymer has a lot of potential to be used, especially to have certain functionality which are still undiscovered. So we can try on metal, we can try on potential energy, and the specific properties of conductive polymer are still there to be explored and more in the future. So just to share with you the findings that we had in the past on conductive polymer is now being used on developing, which is not part of our talk, to be used as a membrane. So now we are developing a membrane to recycle the lithium ion battery. So the idea is that we have incorporated the conducting polymer within the membrane for electrochemical set. And we hope that we can recover the component in lithium ion battery, especially the spent lithium ion battery. So we know that we are moving to electrification. A lot of batteries will be used in the future. If you do solar, you also need battery. If you do hydrogen, you also need battery. But most famous battery is lithium ion battery. But how about the spent lithium ion battery? How we very sure to sustain the availability of the lithium. So what we do fundamentally is that we want to recover as much as lithium so that the sustainability is there. Alright, so with that, thank you very much. Thank you very much.
Thank you, sir. Any questions, please?
Can we think of using these magnetic polymers in drug delivery systems? Drug delivery. Drug delivery. Site-specific drug delivery. We can think of like pacemakers. This morning our vice was talking about pacemakers on a metal sheet and put that sheet with the polymer along with the drug so that the drug can stay longer in the body. Because you have been talking about biodegradable polymers, sorry, biocompatible polymers, right? Can we think of having right?
That's to explore more and more. So, yeah, so from the best of my exposure in the past when I was attached to polystyrene group, we actually do much with drug delivery, but at that particular point of time, we don't really explore having the conducting polymer for drug delivery. But some papers reported a lot on having this polymer. So the major concern is that when we explore conducting polymer is that how this polymer is biocompatible. So now the improvement of the biocompatibility properties of this conducting polymer, most of the conducting polymer. The most biocompatible is PDSS. The least biocompatible is polyethylene, in between is polyphenol, etc. So the wide spectrum of biocompatibility is actually could be tuned for that specific application. This, especially when we have nanomaterials, right? So especially for drug delivery, and if we include this actually I believe can accelerate the transmission and the delivery of the drugs in a specific manner. So I look forward if there is some more question. Say again? Yeah, so we have not yet tested it, but actually the outcome from Daniel's work just now on hydrogel is actually in fact of having tested for our condition. Because we think that so the RBC is also doing only the acceleration of when we want to accelerate the process of moving can actually be promoted by having certain signal. So the electrical signal that the current polymer have can promote those kind of proliferation and stuff. So and so but yeah, we can explore it.
That is Dr. Gujam's presentation. And ladies and gentlemen, since morning you have been observing we are giving mementos, colorful, eye-dazzling mementos to the speakers, right? And these mementos were generously, gifted by Biologic. It's a very promising industry which is meant for designing instruments. Now I request Dr. Pradeep and Dr. Ashish to come onto the dais and join along with our moderators to hand over a memento to Dr. Gujam. My dear students, you are meant for energy. Please give a big round of applause. Now, I thank on behalf of the organizing committee, the moderators for their excellent rendition throughout the session. Now I request Alice to give special announcements for the evening.
We would all break for tea and reassemble here at 4:20. 4:50, sorry, 4:50. Students can join in the lecture and all the guests and delegates in the graces hall. I request the invited speakers and the keynote speakers to just upload their presentations in the PC provided. The delegates who are presenting the posters, kindly be available near your posters for any kind of explanation to be given for the viewers and judges.
మీకు గుడ్డునకే కనపడుతుందా కనిపిస్తే చెప్పండి
ఎందుకు కూడా
అదే
I request all of you kindly seated so that we can start session 3, the last session. I request all the students call your friends. Right. For session 3, this is the last session. I request Dr. Sadasivuni Ashok Kumar to come on there and act as moderator. My dear students, concentrate on the proceedings. Professor Sharma. And there is another moderator, second moderator, Dr. Jalmur. Now he is assessing the post-presentation sessions. Once it is over, he will come back and join as a second moderator. Yeah. We have 3 invited talks in this session. I request all the students please maintain silence and please note down the important points. Thank you. And now I request Professor Sharma to take over the session.
Thank you, this is very well for thank you for the organizers for giving me the opportunity to chair this session. I welcome all of you after the session. We will be listening to the various talks since morning. And now the first speaker of this session is Dr. Rajkumar Velu. He is an assistant professor in the Institute of Technology, Jammu. Let me briefly read about his biodata. He is at present an assistant professor at the Institute of Technology, Jammu. Currently, he is associated and primarily he worked as a research fellow at the Center for Laser-Rated Intelligent Manufacturing. Short way is called as training, University of Michigan, USA. Also, as a postdoc fellow at Digital Manufacturing and Design Center, Singapore University of Technology and Design, Singapore. He completed his PhD thesis in selective laser synthetic of specific bioarmor composites for biomedical application at the Auckland University of Technology, New Zealand. Dr. Velu engaged in research on additive processing since 2001. Its emergence as a new technology and focus on developing materials and experimental infrastructure for fundamental electronic research in this particular domain. Infrastructure development include in-house test beds, consistent research. The focus has been on actual work leading to the invention of new material alternatives, process planning, and enhancements and more. With these few words about Dr. Rajkumar Velu, I now request Dr. Rajkumar to kindly come over, deliver the talk. Yes.
Yeah. It will be a lot. Thanks for your introduction. 3D printing is a new technology. No, it's not a technology. Okay. So it's been working for the last 2 decades. So recently it's been attracted because of analytical model diseases. But this is printing now making a revolution in the industries, not only in any particular regions. So focusing mainly on biomedical applications and aerospace applications. And of course, recently, I could be able to identify a lot of electronic applications as well. So as he introduced, I am Rahman from IIT Jammu. So being an assistant professor and mechanical department, though I am not any chemical engineer or analyst. Okay, so I am a bit apart now from this session. However, I was really closely working with the chemical peoples because the 3D printing technology is a material rendering process. So any sort of materials that need to be rendered through the processing, either by laser or heating source or extrusion method, any methods. So as a 3D printing technology expertise, we always closely work with the chemical peoples or chemical engineers as well as the chemical scientists. So I am coming from Jammu. How to imagine Jammu Kashmir? Right? So this is the history actually. So if you go and watch this movie, this is the history of 1989 to 1990. So, but what is the reality? This is what we are enjoying. Okay. So many things changes in Jammu, and currently we are focusing on development in state-wise as how we are moving forward. IIT Jammu campus, this is our campus. This is a one block, one section actually, and which is an admin block and some engineering blocks and hostel facilities. Moreover, the other blocks are coming in the other place. So IIT Jammu is constructed among various hills actually. So it is a part of each one hill which is allotted for each departments. Okay. So that's how we are functioning. And Jammu, you believe it or not, it's a city of temples. Okay. So most of them might be knowing it, but recently most of them are not knowing it. So this is a general, cultural way of dressing and other thing. But other than that, the beautiful place, okay, which we can see in many other countries like Scotland, England, and other countries. All these things also available in Jammu and Kashmir. And this is, Vaishno Devi temple, which is very famous in Jammu. This is a top of the hill. And this is also some Katra falls is also available. If you visit Jammu and Kashmir, we are going to host you in our IIT campus. So it's most beautiful campus. Apart from IIT Jammu, in Jammu, there is AIIMS Jammu also. So recently the contract was also completed, and we have IIM Jammu, Indian Institute of Management Jammu. So IIT Jammu, IIM Jammu and AIIMS Jammu, three are collaborated, and jointly we are organizing a course also, Medical Engineering Management course. Medical Engineering Management. So all three are included. So we are jointly, all three institutes are jointly working on their directions. So students, those who want to give some other courses like this, you can come and join. And of course, IIT Jammu and IIM Jammu, we have an integrated course, BTech plus PG Diploma in Management. So IIT Jammu plus IIM 5 years courses also. So all these three national institutes in one city, which is in all the other states not available. So in Jammu, we are trying to develop one city. Moreover, all the buildings are completed, their function started functioning. And end of this year, Prime Minister Modi is sitting in all these three institutes to open some blocks there. Okay. So this is some things about Jammu, Kashmir and IIT Jammu campus. So coming to my research experience, as Professor mentioned, I started my PhD from Auckland Institute of Technology, New Zealand, which is bio-polymer-based composite materials and process using different technology. Subsequently, I started working as a postdoctoral research in University of Technology. There, I started working as a continuous then I got an opportunity to work as a research fellow in University of Michigan, USA, there are construction paper in different nanomaterial alloy materials, metal materials also. Finally, I then recently I got an opportunity to do a citizen research associate at University of the same things. So more as a research, we are developing additive manufacturing, which is national technology. Laboratory myself and my colleague Dr. What is the core development? What we are doing currently is we are designing and developing our own 3D machine. As you might be knowing it, 3D printing equipment are pretty costly now. Right? If you go for the last one buy the machines. So over these limitations, we took our challenges of developing our own machines so that we can do a research machine that will not help for extractions, but research steps. And obviously we are focusing on advanced materials like nanomaterials, possible also for high potential applications. Core values we are putting committed collaborative motivations and excellent product quality that we are seeing and more focused on product delivery and on time and on customer response. So and the other objective what in IIT we are focusing is translation research. So more when you see when the research happens, the science and engineering. So we want to make the science engineering more coupled. So that all the technology science development happens at some tier level 1, 2, 3. So we are trying to focus to make lab in the market. So what are the things developed and the technology developed? So we are trying to improve the technology readiness level from 1 to 6 and something like that. So we are collaborating with the industries also to deploy our technologies. So that we can come to the market very easily. That's also our objective. We are going in that direction. So this is my team. I have currently three students and my research staff as well. So they are all working in different technology. So one of their objectives is they develop their own experimental equipments and subsequently focusing on one application and develop materials also. So develop the material sense, basically they are not trying this engineering or manufacturing engineering, they may not be more developing material science. However, we are also collaborating with the medical engineering scientists, national and internationally. So that we are getting a support from them and the material formation from them. Then we do all the process optimization and the 3D development accessibility also. Eventually we focus on the product development. So this is my research based on my projects. So additive manufacturing, what is the status in the Indian context? So what happens is what the data says in 2027 there is going to be a tremendous growth in 3D printing. As I see from the morning, there are a lot of materials discussions happening. But eventually this material, what are the materials we discussed that can be processed into technology for the final product. So there is one way of that can get the correct outcome. So there will be tremendous changes and there is going to be all the companies trying to adapt technology. As I mentioned, the material rendering process. And that is a national strategy for 3D printing. There is a Ministry of Electronics and Information Technology. They dedicated the policies for 3D printing technology in India. So and this strategy mainly focus on Atmanirbhar. So this is the focus. What are the applications we are focusing is healthcare, electronics, and not limited to construction and architecture as well. Then I say it's not only technology. But it's been attracted recently because of availability of software and more of the automation ready materials. So that's just clear. So there are a lot of materials happening. So now these can be focused and print them, get the component of it. And that's the thing. And obviously now some sort of investment focused on 3D printing technology. In 2022, lot of national and international call focuses on 3D printing technology. These are almost 20 proposals. So most of them are rejected. That's the second part. Right. So submitting our rejection, that's what you think of. Right. So additive manufacturing independent technology. There are mentioned earlier. It's a material process. So when I was making classification, this is classical liquid based, solid based, powder based. So coming to this type of processing it, how they are processing it. So based on the polymerization technique, bonding them, melting them, binding them. So again, I just want to connect material process. So based on the material process, we be able to process some for the final product. So these are the different classifications. They have their own definition and properties. And how the material structure can be. Either it can be a powder, or it can be a liquid, or it can be the filament based. So these are the type of material physical structures. Maybe it is the bound of these type of technologies to produce or fabricate a component. So if it is in wire, sheet, rods, pellets, then we can focus on other technology. So these many different technologies currently available, and we now we are currently focused on some of these technologies and develop our own equipments. There are biological applications we are able to please split them into one is non-biological and another biological. Here the polymer is there, ceramic, we can different them for any type of components and biological applications. These are some of the technologies that we are using currently. It's commercially also started. Some hospitals they started developing implants also. So not only in our country, in other countries. So it's been approved. So this is biological thinking. Whereas just before my talk, professor from the legislation talking about the hydrolyzed materials. So those can also be printed. The technique called extrusion-based biothinking. So there will be some cell polymers then across the bioinks will be created. Finally, we can create deposit layer, and then the cross-linking takes place and get a So these are the processes widely accessible also. So this kind of technology currently we are focusing. And we are working on that direction. So what are the other kind of research that we have done and we are working in that direction? So this is a selectively assisted biopolymer composite material. As you can see here, this is a selective laser synthetic machine. So the name has its own definition. Selectively the laser will be sintered. So that is what selective laser sintering. So there is a powder bed and the powder will be deposited. Once the powder is deposited, the laser source, what it will do, based upon the geometry, whatever the geometry we are giving to the computer, it will be selectively sintering and then fused together. Finally, it will be consolidated as one layer. Once the first layer is consolidated, this built platform will go down and there will be another powder will be separated on top of it. So that the second layer will be deposited, then there will be a second layer consolidation happens with the laser. So this is the working principle of laser and this machine, this type of technology currently commercially machines also available. However, we built our own equipment and we started working with the different research created by biopolymers as well for their own implants and biological applications. Generally, we talk about the selective synthetic process. These are steps that we have. As I said, there is a laser motion and the radiation happens. Then the diffusion happens. Then the polymer is flow. Once the laser is irradiated on top of the polymer powders. So that polymer is viscous particles takes place. Then subsequently the solidation happens. And then again go deposition. So this is the complex cycle. But any material or fabricating or printing if you want not really print them, these are the important properties that we have studied going to periphery and optical properties, thermal properties, ionic and other crystallization kinds of things, which is thermal emissions of thermal SLS machines. So this is our work, which is we had homemade selection equipment. This is our homemade equipment and the material selected is polymer and initially we started with PMMA and subsequently mixing the PMMA along with the beta-glycan phosphate to get the partner because we are focused on the bone structures. And we started studying and understanding the materials, whether it has sensitivity or not. Initially, the laser not be absorbed properly, and the deconsolidation is not happen. So we have to understand very clearly about their characterization. Then we started application different composites. Finally, we demonstrated and validated all chemical properties, biochemical properties as well. So this is a setup, this is a laser source, paint platform. These are all assembled by us in the lab. Mainly these are the parameters that we use to control. Because laser power scan speed and bar. So this is the scan strategy here. So you can see here, this is the one scan and second, third. So the laser is moving in the zigzag axis. This is the way it moves, and we use to control all these parameters. As I mentioned earlier, these are the studying characteristics we use to understand about the material, what is heat capacity, glass separation, and activation energy as well. Because when we are processing the laser machine, we need to know these parameters. So these are energy values we use to iteratively adjusting their energy density to get a better quality. This is the initial price. So initially we gave very low power and very high power, high speed. When there is a power output and the laser, and even though high power, if it is high speed, so the laser attraction in the material is very less. So due to that, the consolidation is not happening properly. Then subsequently we adjusted the laser power speed. We could be able to see the complete glass structure based on the laser source. Then we optimize this process parameter to be able to observe the energy density, and this is for the PMM material, polymer material. So we could be able to identify various energy values. Subsequently, as I mentioned earlier, the human bone is the mix of collagen and the hydroxide type. So this is a polymer as well as the ceramic material. So I was looking and trying to understand to mix the PMM plus right phosphate to get better bioactivity. So I think it calls for polymer composites. Again the same iteration happened that BSc characterization. Then finally adjust the laser power and scan speed to understand the material consolidation. As you can see the variations, there are a lot of porosity happens here when compared to the PMM. Because polymer material is there, ceramic material is there. Now the thermal behavior of these two materials is totally different. So ceramic has high thermal conductivity. Due to that variation, it could be able to see the lot of processes. So we need water. So we studied the mechanical property and discussed the porosity because when you are talking about bone-based structures, we need porosity for the extracellular cell. So by default, we are taking the porosity during the resistance process. We are trying to understand those aspects as well. And we studied here also. This is a biocompatibility test to understand biocompatibility because raw material is there, but we process using laser. Is there polymerization happens? So the biocompatibility may reduce. So it's proved that there is no polymerization happens, and it has better biocompatibility as well. But the PMM as well as the meter-type addition, it increases the biocompatibility. So by so finally we proved that need meter-type calcium, a phosphate plus PMM are suitable for the printing processes, particularly the SLS process, without any adverse effects. We had a multi-layer analysis also to understand layer by layer portion and layer by layer system happens. So what is this cross section? How we are really observing happens and how the mechanical properties also we work and what are the those sections how we are different. Those also studied and if there is the energy density is low, then the laser penetration for the quantum is also we have a high energy density. The penetration is much better. So the two layers consumption answer better sensor comparatively. Then I got an opportunity one with the New Zealand Science Center. They came up with they started giving me a keratin powder, natural photolysis, which is made from the sheep wool. And this is science center and what we did started working on it. Initially, once the powder I studied out the thermal capacity and understood. But when I was trying to do the lasering process, the material consumption is not good and it was more fragile and is not suitable for mechanical testing as well. Then I started, blending with other polymers, synthetic polymers, to have a better thermal and to be able to see these different samples and tested and validated. So these are the applications which we have generated from this work. Now, current research is what we are doing is, as far as I was discussing about the synthetic polymers, engineering polymers, is the plastic polymers. And this is a project sponsored by the DST for the dental implants. The objective of this is the thermoplastic materials are treated developably and commercially successful and available things. But however, the mechanical properties is very less comparatively. And when you go for any implants, morning as the metal will give you more toxicity. So to avoid the metal materials, but come to the polymer, the thermoplastics are low mechanical property. So we identified the thermoset material as a candidate material. But now it's a challenge for us. How to process it? Because when coming to the thermoplastic, when you are heating it can be melted and consolidated. But when it comes to the thermoset material, the consolidation, the cross-linking happens. And during in-situ consolidation, it is challenges. But however, we are thinking about the reactive type of thermoset materials. So we call it as reactive SLS. And the main objective is break down the actual process temperature. For example, thermoplastic, we do around 130 to 150 degrees Celsius, maybe more than 120 degrees Celsius. When it comes to thermoset material, when it starts curing. So the first layer, what I am doing is spreading out and again laser source. So the power generation, what I am giving the low power, and this low power makes partial curing of this polymer powder. Then again goes down. Again I am giving a second layer. So now the laser source given. The partial curing is already done, and based on top of the other two powders deposited. The top layer will be partial cured. Again based on the heat, the bottom layer will be slowly getting curing against the top of the other layers. So this is what the idea we have generated. And for this, again the challenging part is the material should be different. Because the one material should be in the powder, right? So the material development is one source, and again we are processing them. Eventually we do the applications. So this is the thermoset material. Initially started working on it. As I mentioned, so the first layer, second layer, third layer. So eventually we start curing it, and based on the heat source whatever we have. This is the process, crystal layer cross-linking, based on our characteristic process. This is a initial experiment which I have done, and we completed the material process. Eventually, we started working on the thermoset and the plastic blending also to get better consolidation. We did all the material. You might be the better person to understand this graph more than and the option setup, which is the 3D printing machine, and we use a laser source, and we are also having in-situ monitoring control also. During laser system process 3D printing it, so we are trying to understand the surface and subsurface features at the porosity level using the in-situ monitoring control techniques. this is the overall process based upon this particular technology. Apart from that, the other ongoing project, this is powder technology what I described, and this 3D printed patient comfort socket, which is almost this year we are completely discussed. One of my pages is presenting more. And this is a real assessment by PSS. These are the current ongoing projects, and this is fund, international fund, which I said existed, and we are also working with additive industries and ad processes, collaborating with Finland. So other research proposals already implemented and assessed. So this year we have submitted the structural protein nanoscaffolds. It's collaborated with Argentina. So they are providing us the protein based for the scaffolds. So this is something in fact currently we are getting into books for different tests. If you are interested, let us know what in the chapters. These are the current collaborators. Currently we are working for the material development. As I mentioned earlier, this thermoset polymer for the powder, all are applicated from for applied polymer science. And as you know, Professor is helping me to develop nano-based materials of their development. And other professors also and other national collaborators also. So we are trying to achieve intelligent-based technology with the product processing, process, and we are focusing on dental, processing success, and aerospace as well as energy applications. So thank you for giving me this opportunity. Thank you.
Another questions.
So first, you're talking about bio-link. So generally, the bio-link, what we are doing is the 3D printability means we want to check the flow of that biopolymer, the bio-link. So the flow and the viscous property. These are the two main properties that we need to consider for depositing on top of the substrate. That's the main thing we try to understand. And the printing happens in the room temperature. We are not heating the bio-link, we are not heating it. The printing happens in the room temperature. And later stage, based upon the material, we'll go for the curing process. During curing process, the water absorption of this will be get off and we get the solid structure. That is for the bio. And second question, sir. For this material, powder material. Yeah, I have the slide. You can see the time. Exactly. Complete yeah. As you can see here, it's a 10 minutes. So this is a line for the complete one layer sintering process. So laser motion it will be like microseconds, all this and milliseconds happens. Then viscous flow and particle evolution in this second. And it comes for the solidification, it comes in minutes.
Just a quick question. I know that the main challenge is to produce it at normally the sample is produced at long time. So the time is required to process the materials is quite long actually. So is there any new initiative to counter this material problem in 3D? Just
yeah, maybe I understand this way. Either you are talking about the product is taking long time. That's what you mean, right? Yeah. Of course, the speed of this 3D printing is pretty challenging now, and we are trying to make it in short duration by giving a coaxial nozzle. We are trying to modify the machine completely so that, for example, multi-material comes to the picture, or we are putting two materials and two nozzles at a time, so that the time can be reduced. So we are optimizing the process technology so that the time can be reduced. That's the one way we are trying to do. And the second way, again, is a material rendering process. So based upon modifying some material properties because as you can see, the solidification time is now very high. So now based upon some other additives may help to do a better consolidation and better solidification time. So that may also be a better approach as far as my understanding. Thanks.
There are no more questions. Let us thank the speaker.
Ladies and gentlemen, you all know that sponsors are very, very important to any event. In a similar manner, for this international conference, now it is starting to be more beautiful because of them. And one of the esteemed sponsors in among us is Mr. Manikandan, Doha Cables. He supported the smart technologies like anything. Please give a big round of applause. And I request Manikandan to come to the dais and join with Professor Sharma and Dr. Sadasivuni to thank the speaker. Now I request him to give a memento.
Friends, our next speaker is Dr. Sorry. I'm sorry. Right. So there's some. I'm sorry. Our next speaker is Dr. Let me briefly introduce him. Dr. is currently an assistant professor at Center for Nano and Material Sciences, JEE University, Bangalore. He obtained his PhD degree in chemistry from NIT, Karnataka in 2014. Later, he joined the Center for Nano and Material Sciences, JEE University, India as a senior research associate, and since 2015, he has been working as an assistant professor. He has been associate editor of University since April 2020. His research interests include synthesis of conjugated molecules and polymers for solar cells, liquid crystals, synthesis of new organic whole transporting materials, and non-fullerene acceptors. So far, he has published more than 50 research articles in the internationally reputed journals like ACS Energy Letters, ACS Applied Energy Letters, Advanced Material Circuit Interfaces, Crystal Engineering Communication, Soft Matter. There are so many more journals of this review. Also, he has 2 Indian patents and 2 book chapters to his research credentials. He is a life member of Asian Polymer Association and the Indian Council of Chemists. In addition, he has the following award to his credit: Seth Young Scientist Award 2015 by Seth Media. Further, he serves as a reviewer for many internationally reputed journals, supervised 2 PhDs and 12 MSc projects. Presently, he is handling 2 sponsored projects funded by Government of India and JEE University. With this introduction, let me invite Dr. Ahipa to give his lecture.
Okay, thank you, moderators, for your nice introduction. And then special thanks to Dr. Kishore. So he invited me over here. So he is one of my collaborators. So I'm from this Center for Nano and Material Sciences. This is actually a research department established in the year of 2012. So in order to promote the research in Jain University. So initially, we have only a small set of group. So started with 12 faculties, research faculties only. So but now we extended our faculty strength to 30 as of now. So more are into the various streams of chemistry aspects, nanomaterials development, and then energy related material synthesis. So along with that, we have nearly 80 plus research scholars in our department, and MSc chemistry is our ongoing academic related work, wherein we used to engage the various subjects of chemistry. And moreover, so far, like once we started 2012 onwards, so far we are able to get the funding from the various research department funding agencies. So far we have 60 ongoing projects, and then so far we have completed 40 research projects, and then this Center for Nano and Material Science usually more into the material development related, but so being an chemistry background, so I am into more into the synthesis part, organic synthesis. So here we are trying to develop a new organic molecule, and this organic molecule can be used as a passivator in order to defect obtained in the perovskite material. So generally the defect is one of the drawbacks in order to get the high efficiency of perovskite solar. In this aspect, we are trying to figure out the new organic molecule which can effectively passivate perovskite layer, thereby eventually get better efficiency. With this intention, so we are trying to develop an organic molecule. So what is perovskite solar? It is a light processing device. So because it is they have an high and balanced charge mobility, high power conduction efficiency, strong and broad light absorption, long charge diffusion level, good solution observability, and composition uniformity and low loss. Because these are there is certain advantages with respect to this perovskite solar. So the perovskite is a light absorbing material, it absorbs the light and then converts it into the electricity. So coming to the materials, so various forms of perovskite are available. So in this case, lead is widely used light absorbing material, where A, B are catalysts and A is an anode. Coming to the working principle of perovskite solar, so here the sun provides the light source. Once it forms on the perovskite material, so electron and hole generation will take place in the perovskite material. So they usually light absorbed by this perovskite, electron jumps into the excited state, then hole will be created in the perovskite material, and once this hole is created, so naively if you provide an electron transporting layer, the hole will transfer the hole transporting layer and then followed by its reaches to the anode. On the other hand, so excited electron will be accepted by the PAO to electron transporting material, and then it jumps to the FTO. So in this is the actual process, therein electron and then hole moves to the respective electrons, and then the generation of the electricity. So various energy levels in this aspect is required. So if you are the widely used light absorbing material is FAPPI3, and then neither aluminum lead iodide will act as a light absorber. And then on the other hand, pyrometal is the well-known hole transporting material. And then so AU acts as an anode, and then TA would act as a EDM layer, electron transporting layer, and then followed by the FTO. So here the metal ammonium lead iodide, if you are using, then minus 5.4 is the valence band, and then conduction band will be at around 3.9. So this is what the energy level states corresponds to the metal ammonium lead iodide. And then the spirometer, since it is a well-known hole transporting material, its energy level of the HOMO should very much match with the 5.4 towards that. There will be effective extraction of hole will take place from the metal ammonium lead iodide. So coming statistics with respect to the efficiency part related to the perovskite solar cell. So efficiency in 2009, so it has an efficiency of 3.10. 3.8, and then it moves the way, and then now it attains like 25.88, the highest efficiency reported in the year of Jan 2023. So there are two types of structural reason. Usually performance also. One is the analytic structure. Here over the FTO, the electron transport material will be coated, over which phosphate will be coated, then followed by the gold transport material and metal will be coated. On the other hand, in case of PIN, this is the inverted structure where over the ITO, the PDOTS acts as a gold transport material, then phosphate, then lithium, then metal cathode. So these are the general two types of device architecture used for the construction of cascade. So we are only concentrated into the development of gold transport material. So why gold transport material is required? Because extract and transport the gold acts as an energy barrier between these two areas. Then improve the device stability, separate phosphate layer from the anode. So these are these advantages. That's why we need to figure out the new gold transporting material. So in search of gold transporting material, we can classify the gold transporting material under the various sectors like inorganic SCM, organic SCM, and polymer SCM. In case of inorganic SCM, the copper iodide, copper oxide, nickel oxide, and so on and so forth will be available in case of inorganic SCM. When it comes to the organic SCM, the pyrometer, carbazole, and so on and so forth will be available for used as an organic SCM. When it comes to the polymer SCM, the PDA and PDOTS, the one can also be used as a polymer SCM. But we are more into the development of inorganic SCM, wherein you can try to figure out any alternative SCM material in place of pyrometer. So in search of SCM materials, so usually the donor, acceptor donor is the design strategy. So we need to figure out which design strategy can give a better pole mobility and better pole extraction ability for the organic molecule. So it has a tunable optical and electronic properties and also enhances the stability. And the molecule has been studied because of easy synthesis and simple structure. It has strong dipole-dipole interaction between the molecules and improves the gold transport capability. The molecular structure can provide a deeper homo level because of the presence of acceptor molecule, which leads to a better PCE, that is power conversion efficiency. So in search of new DAD structure, we figure out that certain molecules can be used in order to get the DAD related molecular architecture. So here in this case TM1, the PCE of PCE is nothing but power conversion efficiency, the 14.15% obtained for this particular molecule. And then if you go for the TM2 and the TM3 and TM4, so because of the changing in the acceptor moiety, so in all these structures, they have replaced the acceptor by simple benzene system by an pyridine moiety in case of TM2 and then pyrazine and then next one is diazine system. So from this case, one can easily understand that the usage of various acceptor systems can influences the power conversion efficiency. And here the donor systems used are benzene, in case benzene and then carbazole, diphenylamine based systems will act as a donor system. And the acceptor in this case is pyridine and it got the highest efficiency, 16.13%. So influenced by this system, so we will try to incorporate the pyridine as one of our molecules and the carbazole as another system. And the energy level obtained for this system is for the TM1, TM2, TM3, TM4 has been listed out, and its HOMO level is very much agreeable with the valence band of the methyl ammonium lead. So because of this, you could able to get the higher power conversion efficiency. So in other literature, it is proved that carbazole carrying an alkyl group. So when alkyl group attached to the nitrogen atom, so usually the usage of alkyl group influences the solubility in the molecule. So with this intention, they have used alkyl chain over the nitrogen
and then they replaced one of the alkyl group with the cyanocontaining group, and then they stated that the cyano-carrying molecules can act as a passivating group. And the efficiency obtained in both the molecules is in one case is 17.9% and the other case is 18.09%. And the energy level obtained for these molecules, the HOMO level, corresponds to the H122 and then H123 system. So it is 5.29 and then 5.29, which is very much agreeable with the perovskite structure. So, and the dotted line represents the calculated value. So these are being calculated through the DFT calculation. In another system, they have used the Sandra system, so with conjugated system, so extended by single and double bond system is present, and it could able to get an efficiency of 18.4%. And the energy level corresponds to this molecule is minus 5.47, which is very much agreeable with the methyl ammonium blood diamond. So these molecules will act as a whole transporting material. By influencing by these type of design strategies, we figure out a motivation for our system. One is spirometad is a widely used whole transporting material, but it has a drawback. So advantages of spirometad is it exhibits the best performance, even though the reported is 25.7%. The thermostability is good, and then soluble in organic solvents, better film forming ability. These are all the certain advantages associated with this spirometad. But disadvantages are high cost for the synthesis and purification. So we are trying to figure out this low cost material which can effectively substitute this spirometad. And the low hole mobility associated with this system, low conductivity and requirement for many dopants like LiTFSI and then TBPI needs to be used as a dopant material. So from this, we landed up with a molecule of carbazole system. So why carbazole? It has a better thermal stability, low cost of the material, high hole mobility, and easy functionalization. So we can do the easy functionalization on the carbazole system at the 2,7 position and at the 3,6 position. So which makes us to take this carbazole as a molecule for our further studies. So now we landed up with this molecule synthesis NK01, wherein we try to use this 2-acetyl chlorine, where this is a donor molecule, and then N-ethyl carbazole aldehyde. So these two will act as a donor molecule, and then we have used acetyl functional group based and then aldehyde functional group based, and try to react with these two reactants in presence of ammonium acetate, ether acetate, 1,4-dioxane at 80 degrees Celsius for 24 hours. This is the method of preparation. We obtained the DAD related design, wherein the donor is chlorine, then acceptor is your cyanopyridone, and then we, on the other hand, N-ethyl carbazole. The yield obtained during this synthesis is 40%, and the color of the compounds we try to visualize under various lights. One is under white light, and then short UV light, and then long UV light. So the compound color looks to be yellow color. So further, in order to characterize this molecule, so we selected for the IR, wherein the cyanide structure is separated into 2.2 centimeter, then CH is structure is aliphatic, this is 2919, then CH aromatic is 3.5 centimeter, along with this 3 double bond stretching at 16.35 centimeter. So this gives us a certain clarity of our molecule. This is can be used as further for transporting capability. Then the mass of peptide is very much agreeable. So LSHB we noted at 478 and molecular weight is 478, which further comes to our structure. Later we have taken this molecule for the NMR study. So proton NMR of this molecule and NMR of this synthesis, which further comes from this structure. And we got this proton, that is hydroxyl group, because this molecule, although the shown is a pyridone form, this can exist in solution there in the two form. One is the pyridone form and another is the hydroxyl form. When it is a hydroxyl form, you can give to identify hydroxyl function with the H on the hydroxyl. So it allows us 1.5 billion. Later we have selected this molecule for the electrophysical properties and in the solution state, and we got 389 nanometer is the absorption maximum and radiation is around 5 nanometer. So in a point of intersection we have used, so that is 4.89 denominator is band gap, 2.89 is the band gap corresponds to this molecule. Under the short UV light and the long UV light, if you examine this molecule, and the long UV light it gives us to be a greenish color. And we were able to figure out the quantum rate through relative process quantum method, and that is a percent in solution there. Later, we have taken this molecule for the cyclic quantum study, where a very early power system. So we used the working capital which we put it on the molecule with the chemical form, and then figure out the oxidation factor, the first oxidation is 1.21, and we use this for the calculation of EO and EO. And the octet is 5.58, where HOMO value of minus 5.58 is very much close to the 5.58. So from this we can say that we can replace the existing 5.58 in terms of energy level matching. Next is the subject is molecule for the DFC study. Using the basic of BPL, 631 gene. So I am trying to optimize the structure and then figure out the normal distribution of this molecule. From the hormone state, the electron density is more localized on the carbon system, and in the case of the hormone state, it is more in the fluorine and then cerebral part. And the theoretical operated values of 5.66 and 2.79, which is very much agreeable with the experimental data. So then we went for the cost calculation by using all the starting materials, and then we tried to figure out for a gram of MK01 synthesis. We were able to figure out that 1,838 rupees is the per gram MK01 is the cost involved for synthesis of MK01. But on the other hand, if you try to check the spirometer cost, it is in terms of $1, $120 to $420. In our case, we were able to get it for the $22.30. So from this, it is clear that if you want to synthesize it, the cost involved for the preparation is less, and it is a single step process. So, but in the case of spirometer, we need to use the multi-step synthesis, and the price is also high. So now coming to the passivation of perovskite, it is well-known fact that perovskite material has so many defects. So which defects formation usually brought down lower the power consumption efficiency, and certain defects they have been listed over here, and the passivation techniques used by the various groups have been highlighted here. So inspired from that, so we quoted our perovskite layer through two-step method, and then followed by the layer deposition of MK01. In this case, we have the pyridone and the cyano group in our molecule. So the formed layer over the perovskite layer, so protects the perovskite from the degradation. So then we subjected this for the photosynthesis study. The absorption properties of the perovskite allow me to show the black line. So it has a wide absorption. So it has a mild absorption. When compared to the other coated MK01 in the various solvent system, also has a wide absorption rate. So it won't affect the absorption property of the perovskite material. And then PL also the study shows that when you coat the perovskite and then over which MK01, the pitching is fluorescence, that means that the form of the hole in case of perovskite has been effectively transferred to the MK01 system. Then we went for the APSM analysis, just to check that the MK01 coated on the perovskite, but it has given the better morphology. So in that case, so the form of the films in the various solvent systems suggests that toluene is the best solvent in order to resolve the MK01. It can protect the perovskite in a better manner. And later we subjected those films for the XRD analysis. The becomes PBI2 formation indicates that, so usually the degradation of the perovskite material. So in case of the toluene used solvent, in the MK01 coated over the perovskite using the toluene as a solvent, the suppression of PBI2 is more. That means the passivation ability of the MK01 is greater extent if you use toluene as a solvent. So with this, I think I will try to end my talk. So thanks to the funding agency SCRT, and then Jain. And this is my group. So one is postdoc, and we are the PhD students. And thanks to the company.
One question. We have time for one question.
Yes, what one? No. So we are exclusively working on the design of new whole transporting material. So using carbazole as one of the molecules. So because in cyano group you know that the carbon and triple bond in N will be there. So N has a lone pair. That lone pair is coordinate over the Pb2 plus side. So in such cases, so the formed layer has an ability to minimize the defects which is formed in the Pb2 plus side. So Pb2 plus if it is free or Pb2 plus is knocked out from the perovskite structure, so usually the degradation starts in the perovskite material. So in order to protect that, if you use an organic molecule wherein the cyano group is present, the nitrogen has a lone pair, those will try to coordinate with the Pb2 plus or vacant sites which is available in the form film. Thereby it pacifies it. Without cyanide, so far we have not tested. So next future work is to compare with the boycotting the cyano group and try to implement forward the reference.
What was the perovskite material used with this MK1? MK1, what is it?
MK0.
What is the material? Perovskite.
Okay, now on behalf of organizing committee, I request both the moderators to please come forward and give momentum to the speaker. Dr. Ravi Kumar, you can interact with sir after presentation, right?
Next speaker is Dr. Sadasivuni. Let me briefly introduce him. Dr. Sadasivuni is the actual name. He has obtained his MSc Organic Chemistry in 2004 from Sri Krishna University, Andhra Pradesh. He received his PhD degree in 2010 from Sri Krishna University, Andhra under the supervision of Professor V. Sumana. He is a research in node synthesis and characterization of chip-based metal complexes and has spectrophotometric determination of antibiotics such as cephalosporins and tetracyclines. He has published 27 such articles in various national and international peer-reviewed journals and presented 13 such articles in various conferences. He authored 2 chapters. Currently serves as a reviewer in various reputed international journals. Presently, he is working on the re-synthesis of metal nanoparticles and their biological applications, including nanodrug delivery. He has completed 2 research projects funded by UGC Zero, New Delhi, and currently working on biogenic synthesis of metal nanoparticles and their biological applications, funded by ERC-RG. Sultan of Oman. Presently, he is working as a lecturer in the engineering department, civil section at the University of Technology and Applied Sciences, Shiraz, Sultan of Oman. Previously, he worked as an associate professor at the Vignan Institute of Technology and Science, Hyderabad. He was a board of studies member or chairman and member for several autonomous engineering colleges in Hyderabad. With this brief introduction, I request Dr. Kodai to please come forward and deliver the lecture. Talk.
Thank you, Professor, for the kind introduction. Good evening to you all. Then I will give you a presentation on facial and leading synthesis of paradox and nanoparticle system. Especially the necessary boards and their anti-accident and anti-cancer and catalytic applications. Today, the overview of my presentation, introduction, objectives and methods used for the synthesis of nanoparticles, experimental results and decision conclusions and evidences. So first we will see here introduction about the nanotechnology. The nanotechnology is very essential for today, solving so many problems in the society because of their concentrated on the fabrication and preparation of the nanomaterial. Nano means the size of the nanoparticles as objectives within the 1 to 100 nanometers. That is the main important criteria of the nanoparticles. That's why they are concentrated on the preparation of the nanomaterial for the different applications, because there are different chemical properties, physical properties, and unique properties compared to the bulk predictions of the very important criteria for nanomaterial. So here they are going to make of the covered nanoparticle for the different applications. So now second one here we have introduced one of the other concepts here, cancer. Cancer is one of the very important problem, essential problem to solve the cancer issues. So one of the death of the population in the entire world because of the only cancer they have been concentrated for the world in terms of the nanomaterial for curing of the cancers. See here, the objective of this material has stopped green synthesis of the green synthesis will be operated for the synthesis of the carbon nanoparticles by using seed pores of the particular plant material. So here we have synthesized material we have characterized by using ultraviolet spectroscopy and FKR spectroscopy and external measurements. We have to analyze for the synthesized material and we have to analysis of the anti-oxidant application, anti-cancer applications as well as the catalytic efficacy of the carbon dioxide nanoparticles of the examine. And finally, we have tested recyclability of the catalysts for investigated this research. Please see here actually the preparation of the nano different methods are available. Chemical method, electrochemical method, physical method, hydrothermal methods, and so many methods are there, so many like that. But we have chosen only micro-synthesis of the nanoparticles because it is a green method, it is a we are using only melasma material as a fabrication and conditioning agents for the fabrication of the nanoparticle. That is the reason that we have chosen the microprocess technique for synthesis of the copper nanoparticles. Please see here, we have taken here this 6-port solution and we have to add copper nitrate solution 1 millimole. 1 mm copper nitrate solution added to the solution of the 6-port solution. We have to subject to the micro radiation within the span of dimensions. We have obtained a brown color solution. The brown color solution we have filtered, we have obtained the residue. After residue, we have used for the material for the different catalytic applications as well as the biological applications. See here, what are the results of here? Characterization, mechanism of the formation of the copper nanoparticle, catalytic applications, and anti-accident activity, anti-cancer activity. So first let's see here. First we have to use spectroscopic studies for the identification of the formation of the nanomaterial, which is the primary tool for the finding whether the nanomaterials are formed or not. We are going to find by using spectroscopy. Then only we will go for the further analysis for the finding the formation material. So please see here, two peaks are there. The first one is the band extract with the originally characteristics observed in the UV spectrophotometer. The peak is pale peak, whereas you see in the copper nanoparticle, it shows the characteristics at the 425 nanometers indicates the formation of the copper nanoparticle according to ultraviolet visible spectroscopy. It is one of the primary investigation for the finding the formation of the nanoparticles. Next one we are going to see here, FDR spectroscopy. The first one is the copper nanoparticle is the red color spectrum. The black color spectrum is the CD pulse black color spectrum here. So you see here what happened here. Some characteristics available here. Black color here I think around 300, 350 OHP available. The peaks are spectrum here. Here the peaks are spectrum here. These peaks are spectrum. All these peaks are spectrum from this material here. Here indicates the formation of the copper nanoparticle by using FDR spectroscopic studies. See here, the external spectrum shows characteristics peaks here. The regular 1 degree, 110, regular 1, 200, 202, 020, 113, 022, 004 peaks available. So the maximum copper nanoparticle orientation in the 110 page. So this external spectrum confirm the structure of the copper nanoparticle structure. Phase stimulated structure according to the external spectroscopic analysis. Please come here, the transmission electron microscopy shows here the majority of the particles are spherical shape, only the few particles are irregular shape from the spherical, the majority of the particles are spherical shape. So maximum nanoparticle formed in this 11 to 15 nanoparticle size is more appear in the TEM analysis after calibration of the histogram. Now let us see here antioxidant activity of the copper nanoparticles. We have checked the antioxidant activity by using ascorbic acid as a reference with the DHSC radical method. Here we are going to check the activity. Here activity increased by increasing the concentration of the copper nanoparticle. Here maximum concentration. See here 110 micrograms here. More increasing the activity of the copper nanoparticle antioxidant activity increase. It will help for the destroy the bacterial growth as well as the inhibition of the bacterial growth, inhibition of the all microbes by increasing the antioxidant activity of the prepared nanomaterials. So here 110 micrograms per ml reaching 79.5% of the antioxidant activity shown by the copper nanoparticles. These are the cancer studies. We have checked the cancer studies with the MCF7 cells. Here also please see here the cell viability decreasing here. See here cell viability decreasing is the activity increase here. At 600 mg per ml increase more micrograms per ml increase the cell viability decreases more activity. So here control the growth of the anti-cancer cells here by increasing the concentration of the copper cell nanoparticle. So the figure is completely concluded by increasing the concentration of the copper nanoparticle, the viability decreases. It demonstrates what happened, the control the growth of the cancer cells. So now I am going to show here the catalytic activity of the copper oxide nanoparticle. In this one, this is the methylene blue we have taken. Methylene blue we have taken only 10 ml of methylene blue we have taken. So the solution we had initially sodium borohydride solution. We have checked the reduction ability, catalytic reduction ability. After 20 minutes, there is no change of any intensity of the peak intensity remains constant after 25 minutes also. It clearly indicates there is a reduction in the presence of the sodium borohydride. This is the first figure. The second figure, what happened to the same solution we added 5 mg of the copper nanoparticle, we had only 5 mg. The reduction was completed within the 7 minutes. Within the 7 minutes, completely the reduction was completed. So the rapid reduction is observed by using copper nanoparticles. The rate constant is 0.37 minutes is the rate constant of the material. Finally, we check the recyclability of the prepared nanomaterials. We have checked here. So we have tested 5 times. We have tested the 5 times. 5 cycles are 84% of the conversion of the material we have observed clearly indicates the catalytic efficiency of the material also significantly remains constant even after 5 cycles also. So it clearly indicates the improvement for the use more times as a recycling materials. See here what the conclusion of this, what we see here. It's economically viable, viable for the preparation, feasible, economically viable, and eco-friendly method, and the board service conducted daily for the structure for the material. Technology showed the 92 containing nanomaterial and anti-activity of the materials species like the disease of the concentration of the copper nanoparticles. Same here, cytotoxicity, activity of species by disease the concentration of the copper nanoparticles. So what are the features of this material? Please see here. The copper nanoparticle effectively used for the treating of the wastewater and treating of the relationship elements contaminated by the organic purification by using copper oxide nanoparticles. Second one, it is used as a biological agents in different biomedical applications. These are the references. And thanks to ERC, got funding from the ERC, and thanks to our DD, and thanks to HOD, and thanks to Juvenile, HOS of section. In addition, we have completed so many projects in nanomaterial systems by using gold nanoparticle with the ribbon. It is under the privilege for the private sector.
Thank you. Short question.
It has the stocks is dependent not the stocks. It will affect subsidies less stocks. Because we use the capital as an activity. So we have synthesis of carbon oxide and particle using more toxins. We have used so that's the cell of both problem and toxicity, but we have using only plant and sex. So then reduce the toxicity.
Thank you. Any more questions?
I request both moderators, please come forward. You may to discuss. With this section 3 of the AOM is completed. Couple of announcements are there. I will request you to pay attention. Especially students, tomorrow proceedings will be in KRC auditorium, and we are expecting all students sharp 8 o'clock in KRC auditorium. And one suggestion to all students is you should sit in silent mode. And some noise is coming because all the proceedings are recording, and during editing we observe some echo. So I request all the students tomorrow also, we appreciate your patience. Tomorrow also you please attend the proceedings and gain knowledge. And I request Alice to give you few announcements.
With this, all the three talks of this session are over. I also believe that this is the last session for today. And I thank also all the three speakers for giving wonderful presentations. And also I thank you for actively participating in the discussions. And tomorrow I can expect more questions
from students or MSc students, they should ask questions. So with this, I once again thank the organizers for giving me the opportunity to act as co-chair for this session. Also, I thank the co-chair for this. Thank you.
ఎక్కడ కేఎఫ్సీలోనా అక్కడ అది బాగానే ఉంటుందా లైటింగ్ బాగానే ఉంటుందా ఇలాగే ఉంటుందా ప్రజెంటేషన్ ఉంటాయి కదా వచ్చేస్తాను అయిపోయింది లేదు జస్ట్ లాస్ట్లోనే వచ్చేస్తాను